Hi Ram, is it audible?
Yeah, it's clear to me. How am I coming on the other end? Is it clear?
Yeah, it is clear, but it is little low.
Low, is it? Okay. Give me one second. I'm just gonna pull my microphone. Is it better now?
Yeah, it's better now. Thanks.
Okay. And, did you have any problem using the link? It was easy,
No,
right?
no, no. Yeah, it is super easy.
Okay. Give me one second. Thanks. Is anyone else?
Not sure. I think we can wait for some more time before we start.
Yeah.
Hello, Ram.
Yeah. Hey, Krishna.
Yeah, hi. I rejoined actually.
Okay.
Yeah,
So,
yeah.
Hi Ram, Alishan here.
hi, Minister.
Yeah. Hi team, good
Okay.
morning.
Good morning, everyone. So we'll go on mute, Ram. You can start session.
Maybe we'll just wait for 2 more minutes.
Yeah, sure.
Because I'm just seeing
Done.
5. I mean,
Yeah.
it's just 4.
Yeah, I think you have a control to mute everyone else. So you better do that.
Yeah. Don't do that. Not sure because I emailed everyone else the link. Um, I sent the link to all the people who were in the initial list.
Mm-hmm.
I'm not sure why people haven't gotten the link.
So how many of them has joined yet? 5.
See,
Five.
Maleshwaran, yourself, Vignesh, and Krishna.
Okay,
I think 5 are there.
Yeah, including
Yeah.
with me.
Yeah.
So Prashant and Deepan, they are trying. So let's just give them some time.
Yeah. Um,
Yeah. I think they're in the group. They're pinging.
is Prasanna going to join? Not sure.
Not sure. Let me see.
Actually, are you recording the video?
Yeah, it's good. Yeah, I'm recording it. So.
Okay, cool. What about Shayan?
I'm trying to call up everyone and to see if they are joining or not.
Okay.
Just now spoke to Prasanna. He is joining.
Okay. I just pinged him too. Does everyone have access to PVsyst at their workplace? No. Is it possible for you guys to look at this over the week to see if you have any questions or not? If you're able to walk through the whole process.
I do have.
Okay.
Not me. I'll just find out a way later how to get it.
Okay. I think you can get if you haven't already tried, you could get a demo for, I think, 10 or 15 days. I'm not sure what the policies are. Yeah.
Okay, let me see. I'll just find out a way to get it.
I think 5th version is right, Machi, if I'm not wrong. That trial version. That time, the other day, you given me access.
You mean the demo?
Correct. That when we are at Sanderson.
Oh yeah, that was the older version. So
Very old version.
we used to have a crack for that,
Mm-hmm.
but not for. Well, I haven't tried getting a crack for this version, so I'm just using it.
Yeah. I'm having currently 6.7.
Okay. Yeah, that's the latest.
That's updated, I guess, right?
Yeah. The person.
Hello.
Hello.
Hey, Press.
Hey.
எப்படிடா இருக்கு?
Good question, but in a wrong meeting.
I see. Correct.
Who are else on the call?
Myself, Maddie.
Prasanna Mallishwan here.
Hey, okay. It's been long time.
Yeah.
I was
Hello,
asking Varman
Prasanna.
to
Ram here.
for conducting this session. Finally, he made it after 1 month.
Yeah, true.
I've been trying to meet Prasanna for the past year. I haven't done it yet.
Oh, I'm better than that.
I have been undercover, man. You can't see me often.
Ram, I think the people who were willing to join, they have joined.
Okay.
I think we can start, and later on. Okay, Ram is calling, just a minute.
Yeah.
Okay, Raj is joining in 3 minutes, he said.
Okay. So I'll just start with a little bit of intro. We're recording it, so if someone's joining at say 15 minutes, let's just ask them to crawl the recording for the first 15 minutes and then look up the video from there.
Okay, Ram, can you just hold your mic closer to your mouth? I think it is okay.
Is it better now?
Yeah.
Yeah, actually, little echo is coming from your end. So if you can cover, that will be great.
Because I'm using my laptop the mic, so that's
Okay.
the issue. I'll try to be as
I
closer
think
to the mic, but if you're
I
having
think
any trouble hearing me, just let me know.
yeah. I mean, better only if you can have earphones, that will be great.
I don't have it now.
Fine,
I had it
cool.
after the last week, so yeah. Okay. So what we'll be doing here is we'll just go through the basics of PVsyst, and what I'm planning to cover here is we all are looking at systems every day, right? We have layouts, we have PVsyst reports, and layout is a different thing, right? You get a request from the sales team or from the design team. You start looking at the location, go use either AutoCAD or SketchUp, and then you get a layout done. So once the layout is done, we're going to generate an energy estimation report, right? Without having a estimation report, we can't do anything, right? We have a product, we don't know how much it's going to produce and what are the losses and things like that. So what we'll cover here is, let's assume we all have a layout. We're just going to generate an energy estimation report for the same. So what I'm trying to do is, the very first layout is something I have here. That's a rooftop system. It's a site in the US. I'll just go through the process one by one. It's a rooftop system. So at first, what we'll do is, I'll just tell you how I choose the meteor station. This part is very important, right? Without knowing, for each and every location has different insolation data. And if it's Chennai, it's going to be sunny. If it's Delhi, it might be a little bit cloudy than what we have here. And if it's somewhere in the US, then they may have much lower solar insolation than what we see at the moment. So that is very important. Once you choose the location and then you choose which data to use, right? Just like every other thing, we have multiple choices even for the insolation data. If you are looking at a site in the US, you have a lot of pre-data that is recorded at airports. They call it TMY3. So what this data does is, they have like a meteor station set up in each and every airport, and then they collect data for say 15, 20 years, and then they provide it to us. And the other set of data you would see is satellite data, which usually comes from, say, for example, Meteornom. Meteornom is not 100% satellite. What they have is a set of algorithm. For example, let's assume you have a ground station in Chennai, a ground station in Madurai, but if you're trying to generate a data for Trichy. So what they're going to do is they kind of form a triangle or something like that, and then they run the algorithm, and then they synthetically generate a data for you that you could use in PVsyst. So that is what Meteornom does, and Sometimes if it's a very remote location and you don't have any ground station nearby, they do use satellite data. And then there are other resources called SolarGIS. I haven't used it. I've come across it, but I haven't used it. It's very common in the European market, and even in the East Asian systems, they use it quite a lot. And then the other one is Solar Anywhere, which is mostly concentrated on the US market for now. It's mostly North American, but they might come to India as well, right? And and then there is this old data provided by NASA. So what they have is they have data for the entire world. Um, is someone out of the earphone?
I think you can mute everyone else.
I'm just going to mute everyone. Right? So yes, I've muted everyone. If you want to raise a hand or something, just ping me so that I know you're having trouble with something. The other data we would see is Solar Anywhere, which is very common in the US, and they're slowly coming into other markets. And old data that we have is from NASA. So that's the satellite data. It's for each and every grid. For I think the grid is like 100 kilometers by 100 kilometers. So if you're looking at data between Madurai and Chennai, it would still be the same. Sorry, Madurai and Trichy, it would still be the same because it might fall within the same grid data. So it won't be location specific. Let's assume you have a site in San Francisco. Okay, San Francisco is a very a tough region because what happens is you have lots of tiny mountain pockets. So, for example, if your system is going to be on the eastern side of the mountain, you're going to have a much different insulation than what you see on the west side of the mountain. So, if you're going to you use NASA data for such a site, then your data is not your prediction is not going to be very accurate. But it also depends on the value of your project, right? If you're going to design a 100 or 200 megawatt project, then it doesn't matter spending 15 to 20,000 rupees on a meteor data. But let's say your whole project you're going to have like say 10,000 rupees as a profit in a project, then it doesn't really make sense to spend all of it on a data. So, so what we'll do here is let's I'll just go through the very first page. So this is what you see when you open PVsyst. Let me do it. So yeah, this is what you see as the opening window in PVsyst once you do it. So we have four different options here. It's preliminary design, project design, databases, and tools. So if you go into preliminary design, you have three different options: grid connected, standalone, and pumping. So the name says it all, right? Standalone is for battery connected systems, and grid connected is for the system that we usually deal with. And pumping is usually for solar water pumping. It needs a lot more detail than what we usually get from the field. So let's just look at grid connected for now, and let's go into project design. Let's not look into preliminary design. Once you have done everything in project design, preliminary design is just easy. It doesn't give you a lot of parameters to operate. It restricts all those. For example, if some salesperson is on a call with you, and they say, hey, this is the project, this is the kilowatt size, and this is what, and I want to see how much it generates. So if you want to see something like that, you don't have to go inside and enter all the module data, string information, inverted, and all those things. You don't have to do any of those. You just have to go there, select the location, and then just input the system size, and then it just gives you a quick number. This is usually to understand if it's even worthwhile going for a market. Let's say we have a project in say Norway. Um, and some days you don't have sunlight, some days you have sunlight throughout the day. So if you want to see if it really works there, you need to have certain kilowatt hours. Let's say you have a house that consumes about 1,000 kilowatt hours a day, and you just do a quick simulation and you see it just generates like say 50 kilowatt hours, right? It's something, but it doesn't really save you any money for the price you pay for solar. So if you want to make any such quick decisions, then I would suggest do it in preliminary design. But let's look at project design for our call today. And then you have an option here called databases, right? So when you go into databases, you see all these details, geographical sites, synthetic Harley data generation, meter tables, and all these. So what you do is, as I mentioned, um, you have weather data, right? You have the meteor station data. And we need to take that into PVsyst so that you could use that in your project. And PVsyst comes with default NASA data and also meteorome, but it doesn't have access to other resources if you have any. So if you have something else, for example, in US, what I usually use is the TMY3 data. And it's not built inside PVsyst. So what I have to do is usually go in and then import the data and bring it into PVsyst so that I could use it. On the right side, you would see component database. So PV modules, grid inverter, batteries, and all those. So, uh, module manufacturers keep on adding new modules to the database, every month or so, right? So when this PVSys was released, what they would have done is updated the database. But, an update is done, say, every 6 months or every 1 year, and your component database would still remain the same, right? It would not get updated as quick as the manufacturer updates their product database. So if you want to add anything, you just go into PV modules and then you bring in all the data. So let's say you have a spec sheet with you, and then you could go and do it. If you don't have a spec sheet, and then there are certain parameters that you don't see in the spec sheet. For example, the resistivity of each and every shunt resistance and all those details are not there in the spec sheet. So it's always a good practice to get a pan file from the manufacturer. A pan file is something that is very specific to the software. So what happens is when it's a very small file, it's not even a kilobit of size. When you import that into PVsyst, it understands, okay, this is the open circuit voltage. This number is maximum voltage and things like that. So it understands and brings in all the detail. So what is the advantage is that you're not generating a not so good spreadsheet, right? Because when you do a simulation, all the parameters or properties of the module is what we actually simulate, right? So if you have entered something wrong, let's say for example, temperature coefficient. So if the value was like say 0.47, and while entering, if you entered like 0.047, so what it means is doesn't you're losing temperature loss by a degree of 10, right? So what happens is if your final loss should be somewhere around 12 percentage, and because of the mistake you made, it might be at 1.2 percentage, and you would be thinking that your system is generating more energy. But what happens is you've done a mistake in the file generation process. So it's always a good practice for you to get the pan file from the manufacturer. And it's easy to reach out to them. When you tell the manufacturers that you're using the modules, it's for say a 100 megawatt project. You want to use their modules, or you want their pan file, and they would be happy to send you. And same with grid inverter as well. You could go and create a few if you want, but it's always a good practice to get the file from the vendor and then use it inside. So let's just go into project design, and these are all the options we have, and we're going to use grid connected for now, right? So before using this window, I would like to show you the project that we are going to simulate, and then a little bit of steps that we take outside of PVsyst before coming to this window. So this is the project I'm willing to use here. So this is a rooftop system. It's located in New Jersey, USA, and I'm using a 360 watt module here, and the tilt is 10 degree, and then you could see all of the details. Azimuth is 186 degrees, and then the pitch, the distance between each and every row is 56 inches, and so you have the address and everything here, right? And the interconnection is at 480 volt. So this is how a typical layout is going to look like, a sales layout. We haven't started construction on this. We are still in the sales phase. We haven't sold this project. So this is what we did with the satellite image we had. And you could see all other details here, module quantity, system size. So if you look at any layout that the team has for which they want to generate a PVsyst report, these are all the details you're going to have, tilt angle, azimuth, module use, number of modules, and things like that. Right. So, and then I'm using an SMA inverter here. This is the project for which we're going to generate a PVsyst report. So the very first step, as I mentioned, is choosing which database or which meteor station, which meteor data to use, right? So what I'm going to do is, at first, I'm going to tell you what I usually do for projects in the US. It's always a practice for us to use ground data, right? Sometimes meteor data from satellites may not be as accurate as the ones we have in ground. It's vice versa. Depends on the area. For example, in India, we have a station in, say, Chennai. And if I want to do something in Trichy, then I cannot really use the station's value from Chennai. I would have to depend on satellite data. If I'm going to use the satellite data from Trichy, that might be more accurate than the ground data in Chennai, right? But for US, you have a lot more ground stations than what we see in India. So I would be finding a station that's closer to this address than the satellite data. So I'm going to use that. So there is a website. It's called Solar Design Temperature. So when you go here, you can see that you have different continents listed here. My project is in the North America, so I'm gonna use that. Right. So what it tells me is this one actually gives me the closest weather station. So the closest weather station for me is located in Newark International Airport. And then there are a few more details here. It has wind speed. It has wind speed. It has the dry bulb temperature, latitude, elevation, and all those things, right? So I'm just gonna keep this window open, and then I'm gonna open a new window where I'm gonna download the data. So this is the website which NASA has put up. Sorry, NRAL has put up, and it has all the stations for each and every state here. So mine is Newark, so I'm just gonna. Okay, so my station is here. I'm gonna click on this and then download. Right. So I know my station is here. So this is my downloaded data. So what I'm going to do is, before going with the project, I'm going to import this data into PVsyst. I'm going to exit this window, and as I mentioned, database is the place where we're gonna go and import this data. I'm going to click on database, and then on all these, I'm going to use import meteor data. So I've opened it now, and you have a drop-down list box here, which has all the data. So what happens is, let me open this sheet and show you what we're going to talk about. Right. So you have a couple of different data here. This is the site address. This is the site name. This is your time zone, latitude, longitude, and elevation, right? And then you have your GHA source, GHA value, uncertainty. So you have a couple of different data here. I think you have 3. I'm not sure. Yeah, I think you have more than 65 data points here. We may use some, we don't use some. For example, we would need GHI and DNI, and then we would need dry bulb temperature. These are all the things that we would usually use for a solar design. But let's say you're sizing up a HVAC unit. In that case, you might need a lot more data than what we need, and you could still use this data. So I'm gonna close. So when you look at this one, it's the very first column is date, second column is hour, and then you have your GHI in column 5, and then you have a DNI in column 7 or 8, something like that. So what happens is when you choose TMY3 here. Okay, when you use NRE and use TMY3, PVsyst understands that when you import a spreadsheet, the very first column is date, second column is hours, and the fifth column is GHI. So that is very important, because every single data has their own format. And if the file that you are trying to import doesn't have that format, then you're going to end up in trouble. Let's say, for example, um, instead of having GHI in column 5, you have it in say column 6, and you have something else. Let's say temperature in column 5. PVsyst doesn't know that. It still thinks that that is GHI and give you a very wrong value. So just make sure that you're choosing the right option. And then I'm gonna choose the file. Right. Okay. So this is where my file is located. This is the file name because it knows what the file name is. It is picking up everything from the spreadsheet. Right. And then AWAC International Airport and then country. So it doesn't know which country it is. I'm just gonna use the top on list box here and then click on USA. North America, source, time zone, and everything. So once this is done, I'm just gonna click on import. Right. The meteor file for AWAC International Airport is created. And then do you want to open the file? Usually I don't open it, but I'm just going to open it for this call. So when you click on yes, what you could see is this data. So, it has all the graphs, it has all the information, your altitude, time zone, lat long, all those things, right? And what you could see here is, let's say, we're going to see ambient temperature, monthly value. When you just click on that, and then I click on, say, month table. So this is the extreme ambient temperature for each and every month, right? So this is something you could use. For example, if you want to see if the data quality is good, you just click on this. Sometimes what happens is, you have a site that's say in Nepal, right? It's way above normal cloud region. So what happens is you would see a lot of spikes. Lot of days in a year where the insulation goes about 1000 watts per meter square. So it's a very bright thing. So what happens is PVsyst might consider that is not very right because um, and then it gives you an error saying that sunlight is abnormally high. Is that normal for the site, right? Something like that. So you could use this agent, but we're not going to do anything with this one now. So I'm just going to close it, and then once you have imported, I'm going to click Save Site. You could see once I imported the file, it says meteor station met file created, right? So what happens is I've imported NEWAC data inside, so my meteor file is created, and then what happens is you have to associate this meteor with a site, right? That is, we haven't done that yet. So I'm just going to click on Save Site. I'm just going to use the same name, and then I'm just going to click, right? It takes a while. Should happen. Okay, done now. I'm just going to close this window, exit this window, and then come back to this window, right? So we are here, and we have a PDF which has all the details of the system, and then we also imported the meteor station that we are going to use for the project. So what I'm going to do is at this page, I'm just going to click on, I already have a sample project here. What happens is, there are a couple of things. For example, your soiling losses, and forget the soiling losses, let's say module data and inward data and all those things. For example, if I'm generating a report for the same customer, I'm just going to use the same data from here and then recreate it, right? So it saves a lot of time. But for now, I'm just going to start a project from scratch. I'm just going to click on the new project option here. So all the options you see here is this one actually helps you look for a project. If you click on this, so these are all the projects I have in my database. So you could just go in and then choose one and then start working on that, right? If you have like an existing project for which you want to change the system size or a module or inverter data, you use this search option. And then the save option is something you do when you change something here, and then you want to save, apply those changes to this project, you use the save option. This one actually deletes the active project, which I'm not going to do now. So what we're going to do here is we're just going to create a new project. So I'm just going to click on plus here, new project, right? Let's do that. So this will be the file name, and then you see something called project name. So what does it mean? So what happens is in PVsyst, so what happens is if you create a project in PVsyst, you save it as a file, right? So you save that, and then you can export that and then send it over to someone in the other team. For example, if Krishna and I are on the same team, and if he is gonna be working on the project later, let's say I'm in the sales team, and then there is a person in the project engineering team, and what happens is if I send over the PVsyst file from my PVsyst to his, so he's gonna import that particular file into his PVsyst, and then when he opens it, he would see all the variants I did, all the modules I've used, all the inverters I've used, meteor station and everything. So that is why we have like two different things here: file name and project name. Project name is something you're going to see on the PDF that we print as the final energy estimation report. So I'm going to use it. And then site file. And this is where we go and search for the site, right? So you have all the sites that this window has all the sites that actually present within PVsyst. You would see some details, some stations which says Meteonom 7.2 station. So these are all the details. These are all the stations that are defaultly present in PVsyst. When you download PVsyst for the very first time, the PVsyst database has all these stations. And then you would see something like NREL, TMY3. So these are all the ones that I've downloaded into PVsyst. And then you have the one in green. So for example, if you import a data for the very first time, and then you come to this window, the one that you just imported actually shows up in green, so that if you want to go check that, you can go do that. Right? So I'm going to choose Newark International Airport and then click OK. So this site is in, and then it's called meteor file, right? Site is something like saying Chennai, and then meteor file is saying if you have more than one source, right? Here you could see that there are two sources here. One is Newark International Airport, the other one is the other Newark International Airport. This is because I already had Newark International Airport in my database, and then I imported it for the second time, so that I'm seeing two options here. But what we could do here is, let's say you have this one is TMY3 database, right? You download this, and then you have let's say you have Solar Anywhere or Clean Power Research. So you use Clean Power Research, and then you download data for the Newark International Airport, and then you import that into PVsyst. So what happens is you have the option to use one between the two. This one will be TMY3, and that one will be Solar Anywhere or Clean Power Research, something like that. So for now, we're just going to use this option, and then click on Save. I'm just going to look at the description. So in the description, if you want to say something about the project, let's say rooftop NJ 360 watt module, 3 kilowatt, something like that. Something that describes the project. I don't even describe anything here. I just use the same file name for description and then close it. This is not gonna be printed anywhere in your PVsyst report. It's just for your reference. So as long as it's clear to you, we're good there. So once I click on save, I get an error saying that orientation is not defined. So within PVsyst, when you see something in red, it means a problem. When you see something in orange, it means that there is a problem, but you can ignore it. When it's in green, you're good to do that. So we see something in red which says orientation is not defined. So what does it mean? Orientation is, this is how you define how your modules look like. How the racking system is defined. So you have a couple of different options here. It says fixed tilt, several orientations, seasonal tilt adjustments, unlimited shed, unlimited sun shields. So these are all for regular systems where it's all for fixed systems. And then you have options here for single axis trackers. All these for single axis trackers, and then you have options for dual axis trackers. So let's look at this rooftop system where we could, let's go to this project, right? So we see here that the tilt is 10.4 degrees and the azimuth is 186 degree. It's a fixed tilt system. It's facing south. It has a tilt of 10 degree, and this is the pitch I have, right? So I go into PVsyst, and then you have an option here. It says fixed tilted plane. So what does this fixed tilted plane? It means that you have like one row of module. Let's say you're looking at a carport system where you have only one row of module, right? Let me open a PDF to show what I mean. So yeah, so this is a carport system, right? And I have only one row of module here. I have the tilt at 7 degree, I have the azimuth is 233 degree, and there is no second row here which is going to shade this, right? When you use fixed tilted option within PVsyst, you don't have the option to actually define the space between rows. So if your first row of module is going to shade your second row of module, you won't be able to define that in. So what I'm going to do is I'm going to use unlimited sheds option, right? So this option, as the picture here, you could see that there are multiple rows, and then this line is actually says, okay, how the sunlight is going to be. If you move this, it means that only after sun reaches this point, this part of the module is going to see any sunlight. Until then, for example, the sun is here, this is going to hit like this, and it goes here. So this part of the module is going to be shaded, right? So what we're going to do is we're not going to use this graphic here and then change the tilt. Instead, we're going to use the input windows here and then change the tilt. I know my tilt of the tracking is 10.4, so I'm going to go and use that here, right? And then I'm going to use azimuth. So you see when I enter 10.4, it rounded it off to 10 because PVsyst, at least for the tilt angle, it doesn't take decimal values. If it's say 10.5, it's going to be 10. If it's going to be 10.6, it's going to be 11. So, and you would have seen some projects where they would have multiple PVsyst. One for a tilt of 10 degree, one for a tilt of 11 degree, one for a tilt of 12 degree. But at least in my experience, what I've seen is you don't see a lot of difference in generation between 10 and 11 degrees, right? And if the racking systems are usually fabricated on site, let's say if someone's welding pieces of steel together, there is much higher chance that we're not going to stay 10 degrees throughout. It might be like 9 degree for few frames and 11 degrees for few frames because it's all just being welded together, right? So yeah, so we have the plane tilt, and then we're going to define azimuth. So this is very important in PVsyst. This azimuth you see here is actually with reference to this north as 0, east as 90, south as 180. You could see that my system is actually tilted to the west a little. It is not perfect south. It is towards southwest. So my azimuth is 186 degrees, right? But in PVsyst, it doesn't take numbers more than 180 because that is how the whole you cannot have like 190. It's all sine and cos within the calculation, right? So what happens is you cannot have a value between after um, 180, right? So you cannot go and enter 186 as your azimuth. So what you do is you subtract 180 from whatever azimuth angle you have. What PVsyst means is south is perfect 0 because this project is located in northern hemisphere. So when you're in northern hemisphere, equator is going to be south of you, right? And when you're in southern hemisphere, you have to look north to look at the sun. Let me try to pull up an image if possible. So let's look at this image, right? So this is how the sun travels, right? This is the equator, and this is how the sun travels. And this guy is in southern hemisphere. This guy is in northern hemisphere. So the guy who is in northern hemisphere, if he has to look at the sun, he has to look south, right? And the guy who is in southern hemisphere, if he has to look at the sun, then he has to look north. So what happens is when you have a project in northern hemisphere, in PVsyst, a perfect south system would be 0 degree. Yeah. So let's go to PVsyst. So what happens is if the system is a perfectly south facing system, then we would enter 0. But our system is not perfect south facing. It has an azimuth of 186 degrees. So what do we do here? One quick trick I usually do is I just subtract minus 180 from all the azimuth I have. My project, for example, this project has a azimuth of 186 degrees. So what I do is I just minus 180 from this, and then I get 60, right? And then I showed you a different project where we have a canopy system, and then the azimuth is actually 233 degree. So what happens is the azimuth for this project in PVsyst would be 53. 233 minus 180 is 53. So we enter that value. If you have any questions regarding this as to why we do that, let's catch up in the question session and then go through it. So for now, let's just assume that you have an azimuth of 6 degree, and we're going to enter that here. And then we have number of sheds. Number of sheds means number of rows of modules you have. When you have more than 2 rows, obviously the rows are going to get shaded, and then you're going to have some inter-row shading rows. But here we have more than 3 rows, and up until 100 shades, PVsyst is going to tell you this is how the shading loss is going to vary. For example, if you have like 50 shades, I'm going to click on the shading graph. You can see this. You can look at the show optimization graph. It says the shading loss is 0.4%, right? I'm going to bring this down to say 10, and then I'm going to click on show optimization. It doesn't change, right? I'm going to move this to 100. It doesn't change. So when you have more than, let's say you have only 2 rows now, it changes, because when you have just 2 rows, the very first row doesn't see any inter-row shading. The second row is the one that is going to see inter-row shading, right? So the shading loss is actually cut into half, so you have only 0.2%. Let's assume you have like 3 shades, 3.3. I think up until 5 or 6, you're going to see 0.3, and then it just goes on to 0.4. But what I know is, I know it's more than 10. If you have enough time, you could just go count it. But for now, I'm just gonna enter 100. Okay. So, and then there is something called as pitch. Pitch is actually the distance from this point to this point. Let me see. Okay. So between two, for example, this is the starting point of my module here, and this is the starting point of the second row. So the distance between these two is the pitch. The one you see between these two is actually the gap, which we don't really use in PVsyst. Some layouts where they mention gap, some layouts they mention pitch. Just make sure that you're looking at the right number and then enter that. So in this layout of mine, I've actually entered what the pitch is. It is 56 inches. And mostly this is defined by the racking solution you use. I've used Panel Claw as my racking solution here, and they have a fixed pitch of 56 inches. So we cannot go and change that. Whereas in a ground mount system where the very first row is not connected to the second row, you can modify it, you can define it whatever you want. In the field you can design with whatever pitch you have, and then just bring that number into PVsyst. So PVsyst has all the values in meters. It doesn't you cannot convert the units into inches or feet or anything like that. It will always be in meters. So I'm going to convert my pitch into meters now. So that's 56 inches, and each inch is 2.54 centimeters. So, right. So this will be my pitch in meters. It's going to be 1.42. And then I have the collector bandwidth. Right? Collector bandwidth is actually the length of this whole module here, right? In this system, my single module is just one, and I have placed the module in the landscape. So the width is 39.25 inches or 39 inches, right? Whereas in the other system, for example, if you are designing for this system, you have 6 modules here, and each module is 77 inches long. So this would be 77 times 6, and then into 2.54 divided by 100. So my collector bandwidth would be 11.73 if I'm doing for this project, right? But we are looking at the ground mount. We're looking at the rooftop project where we just have one module, and I know the width of the module is 39 inches. If you have any spec sheet of the module, just take a look at it. Most 72 cell modules would be 77 inches long and 39 inches wide. So this is 39 inches times 2.54 is 99 centimeters. So divided by 100 is 0.99. So I'm going to enter the collector bandwidth as 0.99. So I do this, and then you have a value that let's say stop inactive band. So what this means is, when I say the measurement of the module is 39 inches, I'm measuring including the aluminum frame or any frame that the system has, so that the module has, right? Usually the modules have a frame. Unless you go for a complete frameless systems like say a Canadian Solar, you're going to have some frame. It may not be 2 or 3 inches long, but you still have some. So I'm going to define these values as 0.02 mm, and then it's the same throughout, right? So I do both, and then I'm just going to click on OK, right? So in the orientation, I've given 10 degree tilt, 6 degree azimuth, 6 azimuth, right? And then I click on show optimization. It tells me that the shading loss is 1.2%, right? And this is where the tilt is 10 degree, and then I have a shading loss of 1.2%. Let's see what happens if my tilt is say 25. I have the same modules, I have the same gap between the rows, and then my tilt is 25 degree. And I go to optimization, it says shading loss 8.5%. And then if my tilt was say 5 degrees, the shading loss would be much lower. It's at 0.3%. So just gonna keep it at 10 and have a shading loss of 1.2%. And then I'm gonna close. So what we have done is we have imported the meteor station, and then we have defined how the modules are going to look like. What tilt, what is the interrow spacing, and all those. And then we're gonna go to system. We're going to look at system now. We're going to define the system size. We're going to choose the modules. We're going to choose the inverters. We're going to tell what is the number of modules we have in series, all the string details and everything, and then close this up. So let's say you have more than one roof. Okay, so what we'll do is let's assume this system is actually divided into two. Okay, this part and this part, and let me just simulate this rooftop first, and then we'll take a system that's a little bit complicated. Okay. So you can name this one anything. I'm just going to say rooftop 1. Okay. For example, you have a system where you're using 2 different modules. Okay. What I would say is rooftop 360 watt. and then I would define another system that says like say 360 watt or 370 watt, something like that. For now, I'm just gonna call it rooftop, right? And then I'm gonna enter planned power. Planned power is whatever the DC system size I see here. For me, it's 1.84 megawatt. So 1840.32. 1840.32. Right, I've done that, and then this is where you choose the brand of the module. Right. Well, the module I have here is Hanwha 360 watt. So I just go here, use the drop down box, and then choose Hanwha. Okay, so I have this. I'm going to choose that, and then so it says 5112 modules, because what it does is here it takes the system size that I've entered, and then it takes the module wattage that I've entered, and then divides it, and then just tells you you need approximately 5,112 modules. Let's say if I enter system size as 2 megawatt. So what it does is 2000 divided by 360, it gives us 5556. So this is the system size. We entered that. They've chosen what module we're going to use. Let's say if you want to, there are some things that we don't want to cover in this call because we would like to get through the basics. But if you want to see the properties of the module, just click open here. It opens up all the details. It tells you what is the short circuit current, what is the maximum current, VOC, VMP, and wattage, tolerance, type of cell, efficiency, temperature loss, and every single thing, size, model parameters, commercial, graphs, and everything. So, this is why, when you look at, say, for example, graphs and things like this, this is why I always suggest that you get the pan file from the manufacturer. Once you do that, you don't have to worry about all these details. Even if you get any of details, let's say for example shunt resistance, series resistance, if you get any of these details wrong, your module may not perform. You're not going to predict the model properly. So let's not do that. Let's try to get the pan files from the manufacturer. So what I've done is we have chosen the module here. Now we'll go and choose the inverter. So I'm gonna go here and then choose. So I have my inverter here, SMA 50 kilowatt, and then I've chosen that, and then I have the inverter here. So you could see that the option here, it says use multi-MPPT feature, right? We're going to use multi-MPPT feature, but at least not for this project. I have all my modules facing the same direction, and all my string sizes are the same. I have 18 module strings for the entire project. So it doesn't matter if my inverter has multi MPPT or not. Let's say for example there are a few conditions. Let's say I have some modules here which are going to be lightly shaded than some modules over here. So if these modules are feeding one MPPT, then probably they might be better because they don't bring down the performance of the entire inverter. But for now, but for the sake of simplicity, I'm not gonna do that now, right? So I'm just gonna uncheck this option. So if you uncheck that option, you could see this value changes to number of inverters instead of number of MPPT inputs, right? So I'm gonna change this to 30 because that is what we have here. We have 30 inverters for the system, right? So I enter 30, and then it changes. AC system size is 1.5 megawatt. DC system size is 1.84 megawatt. To do that. So once you do this section, it doesn't give me any error. So I come to this part, right? So this one says modules in series, and then we have number of strings. So you could see this value varies from 15 to 18, right? So I'm assuming you might all have done string sizing at some point, but let's look at one project. Let's do a simple math here. So as I mentioned, we are going to be using Newark International Airport for this project, right? So what I see here is, along with the other data, I see two different data here, right? The one is extreme low temperature, and then the other one is 2% average dry bulb temperature, which is 34 degrees Celsius. So let's keep these two values in mind, and then do a little bit of math. Okay, let me open a spreadsheet for this. So what does my minimum temperature say? It says minus 15 degrees Celsius, and then the maximum temperature is 34 degrees Celsius. And then we know that we are using a Hanwha 360 watt module. So I'm just going to go. Okay, I'm gonna look at the spec sheet for now. So this is the spec sheet, right? So there are a couple of things that we need to take into account when we size the strings on a system, right? There are two things, VOC and then VMP. And then, it also depends on the inverters that you use. So VOC is the maximum current, maximum voltage that would come out of the module if there is no current. There won't be any power out of it, but VOC is something that we need to size so that we're not exceeding the system, the maximum design voltage. For example, you would have seen some systems where they say it's a 600 volt system, and then some would say it's a 1000 volt system, and then some would say it's 1500 volt system, right? So initially all the PV module systems were 600 volt, and then we moved from 600 to 1000, and then now we are at 1500. Okay. So some modules are rated for 600, some modules are rated for 1000, some are even rated for 1500. And that detail should be there somewhere in the spec sheet. I'm not sure if this module is rated for 1500. So let's just assume that 1000 is the maximum we could do here. And okay. And then I'm gonna bring in a few details from the spec sheet. So VOC is what? VOC for the 360 watt module is 47.71. And then VMP for the 360 watt module is 38.8, right? So these are all this detail is from the spec sheet. This detail is from the site data. Right? Any system, you can define that you can design a system anywhere, be it Chennai, be it in the US, be it in Japan. You always need to take into these two values into account: minimum temperature and maximum temperature. And then once you have taken these details, you're going to start looking at the temperature coefficients, right? So we are looking at VOC, right? So the temperature coefficient is minus 0.28% per Kelvin. So this is percentage per Kelvin. Okay. So what we're going to do is we're going to find two voltages now: maximum voltage and minimum voltage. Maximum voltage is going to be based on VOC, right? So when the temperature and voltage is inversely proportional. When the temperature at a site goes down, your voltage is going to go up. When the temperature goes up, your voltage is going to go down, right? So VOC is the maximum temperature that the VOC is the maximum voltage you're going to see. So what happens is this VOC is based on 25 degrees Celsius. This VMP is also based on 25 degrees Celsius. So what we're going to do is we're going to find VOC for 15 degrees Celsius, and that should not exceed 1000 volt. And then we're going to find VMP, the voltage that the module is going to produce at 34 degrees Celsius, and that one should not be lower than what the inverter accepts. Let's say, for example, the inverter is in standby, and it starts only at 150 volt. Okay, and then your system is only producing 148, 145, something like that. So even though there is some sunlight and there is some power coming up to the module, the inverter thinks that it doesn't have any solar, any current or any power coming from the module, so it would still be in the sleep mode. Okay, so that is why having a proper string size is very important. So what happens is the 0.28 percentage per Kelvin. We know VOC is 47.71, so 0.28 percentage is actually 0.133 volt. So what I'm going to do is I'm going to multiply. This is minus 15, right? So standard test condition temperature is 25, and what we have here is temperature difference. Temperature difference is always going to be 25 minus whatever temperature you have here. Right? So from 25 we're going to go all the way to 0, that is 125, and then after 0 we are going till minus 15. So the overall temperature difference is 40 degrees Celsius. Okay? So this is done, and then I'm going to multiply this 40 by this 0.133. So what happens is I'm going to have a difference of 5.34 volt. So what happens is, since the temperature has gone down, my VOC is going to increase by 5.34 volt. So my final VOC at minus 15 degrees Celsius would be 53.053. Okay. This is VOC at minus 15. Now I'm going to find VMP. So my VMP would also be in the same style, right? So what happens is, so we don't have a value for VMP, but what we know is we have a value for, zoom this a little. And so these are all the temperature coefficient that I took from the spec sheet. Okay. So we had a temperature coefficient for VOC which we used to find the new VOC. And then we're going to do the same for VMP. But you could see that we don't have a separate value for VMP. But we all know that power is V times I, right? So I'm going to use the same temperature coefficient that I see for PMP. It's minus 0. Okay. And then I'm going to find what minus 0.39 percentage means. So I'm going to divide VMP by 100, which is 1 percentage times 0.3. So this will be my addition or difference for each. This will be the change in volt for every difference in Celsius or Kelvin. Okay. So what we're going to do is, we know that the maximum temperature we see is 34, right? So my new temperature, we all know that standard test condition is 25, and the temperature difference is 25 minus 34, right? It's minus 9. So what happens is my new VMP would be minus 9 times this value plus my existing VM. So it's 37.52. So what I'm trying to say here is, when temperature goes down, your voltage goes up. When the temperature goes up, your voltage goes down. So what happens is that minus 15 degrees Celsius, your temperature, your voltage goes up, and what happens is your VOC increases from 47.71 to 53.05. Whereas your VMP, since we are finding VMP at 34 degrees Celsius, your VMP goes down and your new VMP is only 37.52. So the maximum voltage you can have in the system is 1000, right? So you divide 1000 by your new VOC, which is 53. So you get 18.84. So what this means is your maximum string size can be 18.84. You cannot go lower than that. So this is your maximum string size. I'll just minimize the spreadsheet now. We can come back to this later if you have any question. Let's look at the thing. So this is why we have 18 here. I may not have done a good job in explaining how we do the string sizing. We can go back to that later, and make sure that everyone understands. But for now, you see minus 15 and 18. So this is how PVsyst calculates this range. This 15 actually comes from inverter data, and this 18 comes from the calculation that we do now. Everything PVsyst does can be done in a spreadsheet outside of PVsyst, but it just makes your life easier, right? You just choose a 360 watt module. It says 18 is the maximum string size you can have. If you're gonna use a 270 watt module, it says 23 is the maximum you do here, because a 270 watt module might have different open circuit voltage and different maximum voltage. So that is how it calculates, and it just does in a fraction of a second, for which we might take closer to a minute or something. Let's go back to the module that we chose. 360, 18, and then it says 284 because this is the number of strings that we're going to have. I'm going to go back to the design. So I have 5,112 modules. 5,112 modules, and then each and every string is of 18 modules. I'm going to divide this number by 18, so it leaves me 284. So that means I have 284 strings in my system. I'm going to enter that here, 284. So this thing is all done, right? I'm going to close this one. So we have defined orientation, where we say what does the module tell, how the module looks like. And then in the system, we have defined the system size, module type, number of modules, then inverter type, strings, and all those details. So once we're done with that, we're just going to go to detail losses, where we define other detail losses. So this section is a bit important, but it involves a lot of input from our energy estimation team. Okay, because all the values you enter here are assumptions or studies that have been done in the field. So this is where we usually depend on companies like DNV. They come to our power plant, they take a look at every single detail. They take a look at the modules that you have used, the wire length and all the voltage drop and everything, and then they give you, this is your ohmic loss, and that is what you use in PVsyst to generate a report. But let's see what values we use, because we haven't built the system yet. We don't know if we are gonna win the project, but we're just doing energy estimation report to understand how much the system generates, and we are gonna use some of the assumptions here, and we'll see why we do that. So you could see UC and UV values, right? So what happens is UC is something, UC is for conduction, heat loss from conduction, and UV is heat loss from convection. So conduction is when you have something in contact, let's say you have a pressure cooker, at home. It's hot, right? So when you touch it, you feel the heat, and you're feeling the heat because of convection, right? You're in an AC room, you're feeling cold. You're not physically in contact with, say, the air conditioner, but you're still feeling cold because the air around you is kind of cold, and you're feeling the cold wind. That is convection. So what happens is, PV module, as we know, sunlight has two components, right? One is heat, the other one is light. Our solar water heaters use the heating component. It doesn't use lighting component. But our PV modules, we only need light. We don't need the hot sun. So heat is actually bad for us. When you have a project, say in Rajasthan, you're going to have a lot of loss due to higher temperatures, higher ambient temperatures. Whereas you have a project in, say, Siberia, right? The surrounding temperature is very less, so you're not going to see that much of a loss due to temperature. So what happens is, we are going to define all the values here to say how much of heat loss your system is going to have. This 20. So when you have a system, for example, let's assume you have a carport system like I have here, right? This carport system actually has 8 feet of clearance. You could go and stand under this carport. So what happens is there is lot of area for the wind to move around, right? If the module is getting hot during the day, there is wind flow at the bottom, it just takes the heat away, so you're not losing a lot of energy. I mean, you're not your lot of heat is actually sent out. Your module is not getting hot. Whereas in a rooftop system, we don't have that luxury, right? The tilt is just 10 degrees and the clearance is just 12 inches. So there is not enough area for the wind to move through the modules and take away all the heat from the modules. So what happens is in turn, you start losing a lot of energy due to temperature. So what happens is this one, the value you see is 20 and 0. I haven't done the whole math, but the value I get from my design team is to use something like 20 and 1.2. So what this means is 20 is 20 is the factor by which I lose the heat through the material that is connected to the module. For example, I have like a aluminum frame connected to the module that takes away a little bit of heat from the module. I might have, say, a fiber frame connected to it that might take a little bit of heat from the module. So it really depends on what type of frame you use and what all study that the design team has done before, right? So I'm going to give 20. And then this value is 1.2, wind loss. So there is going to be a little bit of wind movement beneath the module, but it is not super high like you see in a ground mount or a carport system. So I'm just going to keep this at 1.2. You would have seen some projects in residential scale. In residential projects, we don't have any gap between the modules. It is going to be flushed onto the roof. So in those projects, you don't have any space for the air to move. So it doesn't take away any heat from the module. So in those cases, this loss factor might go down. It might be like 1.0, sometimes even 0.5. Okay. So this value, it's an assumption. This value has to come from the design team, or at least people need to sit together and understand. Okay, this is what we do. And this is how the whole process is done. So these are all the factors that usually independent engineers like DNV and Lidos define. They have people who sit in the field. They have different measuring methodologies. They might have more than 4 thermocouples on each and every module. Take data from that, study the data for the whole year, and then give us just 2 different values that we could use in our energy estimation. So let's say if this was a carport system, like you see here, if it's a canopy, I know I have lots of area for the wind to flow through, so I'm just going to use 25 and 1.5. This 25 and 1.5 is actually defined by the independent engineers, and it's been agreed upon. When you use 25 and 1.5, because it's a carport system, the independent engineers are not going to come to you and ask, hey, why did you use that? But let's say if you have used like something like 35, then that's a questionable number that we use. What happens is when you say 35 and 1.5, you're not going to see any loss because of the modules getting hot. But what happens is system might not produce. Our goal is to predict what is going to happen, right? For example, you may say that the system is going to produce 1000 kilowatt hours now, but if the system is producing only 850 or 700, then obviously we are the ones who need to be answerable in the later stages. That's because we haven't done good assumptions now. So what I'm going to do is I'm just going to use 20 and 1.2, which is something that they have set a standard for rooftop systems, and then I'm going to leave it at that. And then I'm going to look at ohmic losses. Ohmic losses is all the loss due to resistance or voltage drop that you have in the whole system, right? So right now we haven't wired the system. We don't know how much, what is going to be length of the wire from point A to point B, and what is going to be the voltage drop in that. So we don't know the exact value until we actually go and install the system, or until we do all the wiring, right? So, but we know one thing: we don't want this loss to exceed 1.5%. Right? I'm not sure how many of you have taken a look at some of the tenders that come in. When the project goes out for a proposal, when the project comes in for a proposal, for an RFP. If you take a look at it, they have certain requirements. Right? The customer would say, I want to produce so many kilowatt hours. I want to use tier 1 modules. I want to use tier 3 inverters. And then they also define certain factors. In those factors, you would always see something about the voltage drop. or the ohmic losses, they would say I don't want to see more than 2% voltage drop. So what happens is the voltage drop usually arises from the current traveling from point A to point B, and you have a wire, right? So what happens is if the wire is not wide enough to take all the electrons, then you're going to lose some to the some as heat, right? So if you have like a very wide wire, then the electrons don't have any trouble passing from point A to point B, and they're all happy, and they just all of them travel without generating much heat. Just like the traffic jams, right? You have a wider road, you don't have any problem. All of the electrons, all of us in the road are happy. If the roads are not wide, if they're congested, then obviously we're all super mad and everyone's hot, right? So so it all comes at a price, right? If you want to have a wider road, obviously you have to spend more. If you want a narrow road, you don't have to spend more. But what happens is you have losses in other terms. People reach the destination late, things like that. So same thing applies here. You have a wire which is much wider. It is expensive, but you don't have loss. You don't have higher losses. But if you use like a thin wire, obviously it costs less. But what happens is you're having little bit of loss. So it all comes down to a balance. Let's say you're losing 1% due to using thin wires, and the overall loss in energy is say 1,000 kWh, and each unit is 3 rupees. So maximum is 3,000 rupees loss. And if the while designing, you understand that going for a thin wire saves you 10,000 rupees. Okay, so you make the decision. You're saving 7,000 rupees by going for a thin wire, whereas you spend 10,000 rupees and then you see better performance. Whatever balance works for you, please do that. So I'm gonna use a default value of 1.5. Some places I've seen people use even 2, but let's just stick to 1.5. So this is on the DC side. This is from the module to the inverter, and then you have from the inverters to the interconnection point. Right? Sometimes the inverters are located close to the electric room. Sometimes they're located on the rooftop, and then we bring all the wires down to the electric room. So whatever it is, so just assume like we're going to have say 0.5 percentage. Um, we are saying 1.5 percentage here because the voltage is high, right? On the DC side, you are going to design a system which is 1000 volt. Whereas on the AC side, we are going to see something like 240 volt. And 240 volt it travels like 3 wires. You have a three-phase system, so 240 is again in 3 wires. So you don't have as much as loss as you see in the DC side, right? Um, this is the classic example. Why do we have transformers, right? We get powers at like 11 kV, 33 kV, and then it all steps down 240 volt at home, right? We all could ask why aren't they transmitting all of the energy at 240 volt, right? They could do that, but they would be much loss in the wires. That's why every time they transmit powers in like 11 kV or 33 kV, and then they have transformers and then bring it down to 240. And that is what's here for. The same principle applies here. You're using 1.5 percentage here because on the DC side, voltage is really high. You're close to like 1000 volts, so you're seeing much higher voltage drop or loss due to that. And then on the AC side, you're just seeing much lesser loss, 0.5% like that. And we don't have in this project. I don't have any transformer. My inverter output voltage is 480 volt. So and my interconnection voltage is also 480. So I'm not going to use a transformer in between. But if I'm going to use a transformer, I'm going to click on this option and then enter some value like 0.2, zero point 0.9, something like that. You know, these values I would always suggest you check with the transformer manufacturer. Tell them that you're going to use these parameters in PVsyst and ask them what is the iron loss and what is the inductive resistive losses to them. If you have any of, for example, having a value as zero point 0.2 or zero point 0.3 makes a lot of difference in the final generation, right? So please make sure that you get these numbers from the manufacturer. Tell them you're using their product, so they need to give us the data. So I'm just let's assume we're gonna use transformer for this project. I'm gonna leave this one on, and then I'm gonna close this and then go to the next tab, which is module quality data. Right. Module quality, this is module efficiency loss. So what this means is, let's look at the spec sheet of the module. So what do they say here? So you have all these data like power, 360 watt, 365, 370, and all those. And then you have a detail which says power tolerance. So power tolerance is 5 volt to 0 volt, 0 watts. What this means is, even though the modules are all rated for 360 watt, not all of the modules are 360 watt. Some might be a 361, some might be a 358, some might be a 365. So what happens is, we want to make sure that we are, for example, recent times, you could see the number here. It says power tolerance is 5 watts to 0 watts. But if you look at spec sheets from say 2001, 2002, you will see two different numbers here. You will see 5 watt and you will see 3 watt here. So what that means is, when you're buying a 100 watt module, it could be anywhere from 97 watt to 105 watts. Okay, and what people are taking advantage of that, instead of giving you 100 watt module, since it's already stated that it could be anywhere between 97 to 105, they were sending all modules at like 97, 98, 99, but not 100, right? So what happens is, you have a system of 1 megawatt, based on the STC value. Let's say you have 10 modules and you have designed it saying that it's all 100 watt modules, so it should be a 1000 watt system, right? But what happens is, all the modules we received were at 97 watt, right? And so the final system you have is 970. It is not a 1000 watt system, but it's a 970 watt system. So obviously your system is going to generate much less than what you thought it would generate, right? So in order to avoid that, in order to make sure that the manufacturers don't cheat the customers anymore, we don't have negative power tolerance. We always have positive power tolerance. So when you buy a 360 watt module, the minimum watt the module would have is 360, and the maximum is 365. It doesn't matter. The guy could come to you and give you 3610, 370 watt module. We won't complain, but he's at a loss, right? So what the best thing he could do is make sure that the modules are 360 watt. And another thing is, when you buy a module, you don't buy it per piece. It's when you look at price of a module, it would always be like 6 rupees, 60 rupees per watt, 70 rupees per watt, 80 rupees per watt. It doesn't tell you that a module costs you 1000 rupees or 2000 rupees. It would always be based on per watt. Okay. So what happens is, there is a manufacturing defect. Let's assume there is a manufacturing defect, and all the modules that you get are actually 362 watts instead of 360. But in the spec sheet it would say 360, and that is what you are going to pay for. Okay, so let's say, each and every, you go to a vendor and then he tells you that the price of the module is 10 rupees per watt, and you want a 360 watt module, you're going to pay him 3600, even though the module is a 362 watt. The spec sheet says 360, so you're going to pay only 3600. So the module manufacturer makes sure that he doesn't give you a continuously of 360. But there are, these are all manufactured, right? The modules are all silicons, so you cannot define it exactly the way you want. You have done maximum, but there is still 0.0001 percentage of changes in the structure. So what happens is, you have modules ranging from 360 to 365. So what happens is, when you order modules from the manufacturer, he does a flash report for each and every module, right? So if you're going to order, 1,000 modules, he's going to send 1,000 different spreadsheets where he has done a flash test, and that will give you the VMP, VOC, IMP, and ISE for all of the modules, all 1,000 modules. So what happens is, you are going to see module wattages ranging from 360 to 365, as I mentioned. Okay, so what does this mean? So let's say you have a 365 watt module, but whereas the spec sheet says 360. So what does this mean? So what does this mean? It means that you have a gain of 1.3%, right? So if you have something like that, I'm going to enter minus 1.38, because this one says module efficiency loss, but it is not actually loss, it is a gain, right? So I'm going to enter a negative minus 1.3. But in reality, it is not the case, right? We won't have all of the modules at 365 watts. let's assume we're going to receive only 50% of the modules at 365 and rest is all going to be at 360. So it's going to be like 0.2. I'm going to go and change this to 0.7. Okay. So this is an assumption. But when you are going to build a system, when you're going to go and install the system, you have received all of the modules from the manufacturer. You have the flash data, you have the module wattage data, so you know what the module wattage is. Let's say, for example, we are ordering 10 modules, okay, and then the values range from, let's say, okay, we have ordered 10 modules and values range from 361, 362, 360. 365. Okay, so what is my sum here? Right, so 361.4 is the average, and my my spec sheet says 360, so I'm just going to divide it by 360, right? So 0.38%. So this is what I'm going to use here, minus 0.38, right? So this is how they do. But if you have like 10 modules, you can do this. But when you're going to order thousands and thousands of modules, we won't be able to do this. It has to be someone who does this for us and just give us the flash data. So it's minus 0.3. And then LAD loss. You would have come across this factor. It's light induced degradation. So what happens is, the modules are manufactured. They are sent to the field. When they're exposed to light for the very first time, there is a little bit of degradation in the performance that you cannot claim back. It'll stay like that for the end. For example, when you order a 400 watt module, right? You have like 1% LAD loss. So what happens is it actually loses 4 watts on the field. So it would always stay as a 396 watt module. It doesn't stay as 400. So that loss, whatever you have in the spec sheet or whatever the manufacturer tells you, you enter that data here. So I'm just going to click on default. But usually what happens is you talk to the manufacturer and try to get the values. Manufacturer give you something like, okay, minus 1%, or 2%, something like that. So I'm just going to click on default for now. But that detail has to come from the manufacturer. These days we have a lot of manufacturers who try to make changes in the manufacturing process so that they don't really have any light induced degradation. There were a few companies which recently came out and said that they have LAD proof modules. The modules that don't have any LAD losses. So what happens is you buy a 100-watt module and LAD loss is like 2%, you're losing 2%. So the module that you have in hand is actually 98 watts, right? But you would be paying for 100 watt, you would be designing for a 100-watt system, so you are at a loss of 2%. But let's assume there is a guy who manufactures 100-watt modules and says that there is no LAD loss. So obviously, you're at a gain of 2% than going for manufacturer B than doing with manufacturer A. So let's just enter default value here. Let's just keep it as it is. And then this value is power loss at MPP. You could do this calculation a little bit in detail, but usually it's assumed to be a default of 1%. So what the power loss at MPP means is that, as I mentioned, not all modules are made the same, right? Some modules have a different VOC and some have a different VMP. Even though they're all rated as 360 watt modules, you're going to see different values. You're going to see different performance for those modules. So there's going to be a little bit of mismatch between the modules in the same string. When you have, let's say, you have these 10 modules in one string. Okay, this 365 watt module is going to generate more than 360 watt module, right? So there's going to be a little bit of mismatch, and that mismatch is what we account here. And frankly speaking, is a little bit difficult unless you have string monitoring systems for each and every string. It's going to be a little bit difficult to account that. So I'm just going to keep this at default as 1%, and then the string voltage mismatch. So these two values, the one has to come from the inverter manufacturer and one has to come from the module manufacturer, but usually they don't provide that. So I'm just going to keep it at default of 0.1 and 1%. In the field, you cannot you cannot you cannot get rid of these mismatch losses. Okay, there are going to be mismatch losses, but we need to account for those. Let's say for example you say there is 1% loss, and then the loss is only 0.5 percentage. It doesn't matter. Your system, as long as the system is generating more than you have predicted, no one is going to come and question us. But let's assume you just assume that there is no power loss at MPP. It says there is no mismatch losses, and then you see a loss of 0.5 percentage. Obviously we're gonna be questioned. When you look at the final production number, it doesn't tell you. I know when we all have looked at systems monitoring, right? It doesn't tell you what is the loss of temperature, what is the loss of mismatch and things like that. It just gives you a final megawatt hour or a kilowatt hour, and we look at that number and we are like, okay, we have predicted 1,000 kilowatt hours. The system has produced only 980. Where is the 20, right? Sometimes systems are physically down. The inverters are busted, and the inverters hasn't operated for like 6 days. So we know, okay, this is loss. But let's assume there is 365 days. There was no downtime. System was active throughout the year. The meteor data that you used is all good. It's pretty much the same, and then you still see some loss. So that's where all these factors come into play. There might be some mismatch losses which we cannot really go and analyze and find out. So that I'm just going to use the default 1% and 0.1% here. And then there is something called as soiling losses, right? So the soiling loss is actually studied in detail. It depends on how many rainfall events we have in a year, how many times we are going to go and clean the panel and things like that, how many snow events and things like that. So there needs to be someone from the meteor side who does the study for us and then generates the data. So while at Sun we actually have a tool. Let me show you that. I'm not sure if you had a similar one for the sites in India, but at least in the US, we worked with the independent engineers, and then we got a tool. So what I'm going to do is I'm going to enter the address. So I'm going to enter Newark, New Jersey. Right. I do that. It's fixable lat long elevation, and then I'm going to click on find closest station. So I've done this. So what I'm going to do is I'm going to change the details here that says rooftop, and then send the detail 186 azimuth, and then I go to the next tier and click on run snow loss. Okay. So I get a value for the whole year, which is 8.6%, 9.1%, 4.8%. So it goes like this. So then we take this detail, and then we go here and just put like, okay, 8.6, 9.1, 5.1, 2, 0, 1. Whatever values you get. But what happens is usually we don't have access to such good details here. So I would go and assume, if it's right by the road, you're gonna have a lot of soiling losses coming in, vehicle pollution and things like that. So if you don't have anything like that, just put like 5%, 6%, something like that. Do this, and then IAM losses. So hey guys.
Hey, Machi.
I've unmuted everyone now. I didn't realize if anyone had any problems. So do you want me to slow it down, or how is it so fast? I should have checked in long back, but
Yeah, we are good. No worries.
I'm just writing down the points which I would like to ask while asking the last question.
Okay. Okay. Cool. Cool. And how about everyone else? Are you guys good, or would you guys like to go back to some of the topics, or do you have trouble in any of the topic? If you have any questions on, say, the string sizing and the other details that are not related exactly to PVsyst, but in our design in general, we can definitely go back to that and have those questions answered later. But if you think that not understanding that particular point is stopping you from understanding the next steps in PVsyst, then definitely let me know. We can go back to that and look at that.
Sure, Machi. You carry on.
I'm gonna mute everyone again, but just send a text or ping in this one if you have any questions. So IAM losses, it means incidence angle modification. So what this means is, the sun rises throughout the day, right? Early in the day, sun is at, say, sea level, and then during noon, it really goes up high in the sky. At one particular point, the sun is going to be exactly perpendicular to the module. That is when you're going to have a lot of sunlight going into hitting the module, right? Because you have like a glass in front of the cell, in front of the PV cell. So obviously, what happens is some rays don't really go all the way into the glass and hit the cell. Some are lost due to reflection, some are lost due to refraction. So this graph here actually takes into account all of those. And this study should be done by the PV module manufacturer, and that detail is actually built into the pan file, right? Because you won't see any such graph in spec sheets, so we won't be able to build any of those. So what we need to do is we need to get the pan file from the manufacturer, and they would actually build this whole model into the pan file. So and then you have something about auxiliaries, aging, unavailability. So what I'll do is we'll cover these details a little later. These are not needed for regular PVsyst simulation. Unless and until you're doing a very detailed simulation, you wouldn't need those. Let's not look at auxiliaries, aging, unavailability. Maybe we can have like a separate session later to look at these details in these tabs in detail later. I'm just gonna. So we have defined thermal parameter, we defined ohmic losses, we defined LID mismatch losses, soiling losses, IAM. So I'm just gonna click on OK, and then I'm not gonna talk about these for now, the horizon, near shading, or miscellaneous tools for now. I'm gonna go to run simulation. So we have defined the orientation, we have defined the system sizes, modules and things. We have said what are all the losses. So now I'm gonna click on advanced simulation, right? So I'm gonna go here and then enter the details saying that okay, simulation 1 or whatever it is. Let's say for example, you're gonna look into multiple variants. Let's say at first you're gonna check with SMA inverters, second you're gonna check with say selector inverter, third you're gonna check with a different central inverter. You're gonna use this tab here to enter those details so that you know what you're looking at. Sim 1, let's say SMA, and then I'm going to click on simulation. So once I have done with the simulation, this is the graph I have, and then you have an option here which says report. So I'm going to click on report, so you get this final PDF report that we usually see as a PVsyst report provided to us, right? So you can see it says version, date, grid connected system, and then it says rooftop, New Jersey, 360 watt. So whatever definition I gave there in the top, you say I said that's a 360 watt model system. For the description, it comes here, and then the geographical site, That one comes here, and then all of the meteor data, Newark International Airport, source, albedo value, time zone, all those comes here. And then the second one is simulation variant. So in my sense, I named it as SMA. So I'm seeing that one here, and then simulation date, time. Right. So this one, simulation date and time, is very important because let's say you're looking at a PVsyst report for a project that was constructed lately. Let's say the installation was done in say April, but the PVsyst report is from January. Then obviously it's an outdated energy estimation report. Why I'm saying that, because during the construction phase, we always change certain parameters. We may have encountered some problem with availability of 360 watt modules. Let's say we want 5,000 360 watt modules. Finally, we would have ended up with like say 4,500. We may have trouble finding the other 500. We go and use a different set of modules. So always make sure that the construction date and then the energy estimation date is right if you're going to review a project. So we have this date here, and then we defined unlimited shed, we defined the distilled, azimuth, spacing, and all those values. So we did that, and then here you would see all of the information about the module, right? We chose Hanwha modules, string size was 18, we had 284 strings, so you have this whole system size here. And then same with inverter, we defined why am I seeing 28 units here, because I think I didn't do a good job when defining the inverters. It should have been 30, but I'm seeing 28 here. So actually I've missed entering 2. So what I'm going to do is I'm just going to close this one, click on this back button, go to system, and then go and change the number of inverters. Okay. So I've done that. I'm going to click OK, and then come to advanced simulation and click on simulation again. So I'm opening the report again. I know we have checked till here, everything was good. So I'm checking the inverter details here, 30 units of SMA 50 kilowatt inverter. The thing is here, and then these are all the details that I entered. Array soiling loss is 5%. That's what I entered. This one is 21.2 is what I entered, and then all of the values that I entered here, 1.5%. LAD was 2%. Auto was -0.3. So I entered all those values, and that is all right. So in the first page, you wouldn't see. The first page is just to make sure that the report has all of the values that you entered. So same with page 2 as well. And then third page is where you start seeing the simulation values, right? So you have all these details here, and then you have a number that says produced energy. So this produced energy, it means how much energy you generated in this year, and then you have the specific yield, which is like 1246 kilowatt hours per kilowatt peak, and then you have the performance ratio. So and then you have this graph, which is very common. You guys would have. Right? So you have this graph which says YF, this is the produced energy, these are all the losses, and these are all the system losses. So you do that, and then you have a table which has GHI, DHI, ambient temperature, global incident, global effective, and E array. So E array is what the energy that you produce in the PV module, right? Whatever energy, in sunlight, whatever energy is generated on the module side. And then E grid is something that is fed to the grid. So the difference, you see a difference between this value and this value, right? That's the difference, that's the loss you actually have in the AC side of the system. And we'll get to the next page where we have this graph and I'll explain you what everything here is. So this 1422 kilowatt hours per meter square, this is what you see, this is what the insulation data is, So if you're looking at a site somewhere in India, this one would be around like 2000, 2200 because we have a lot of sunlight. And this horizontal global irradiation on a collected plane. And this is global incidence on a collective plane. So this means the energy that you actually collect on the PV surface, right? We have kept it at a tilt of 10 degrees, right? So what happens is when you keep something in the floor that is facing exactly north, exactly at the sky, it doesn't collect any of the scattered beams. So when sunlight reaches Earth, you need to understand that there are three things here. Whatever sunlight we get from the sun, we call that GHI. That is all of the sunlight that we get. Okay, and this one is divided into two parameters. The first one is direct normal, and second one is the reflected beam. Okay. Direct normal is something we see when we look directly at sun. For example, you go out and you look directly at the sun. We cannot look at it because it's bright. And all of the beam that our eye sees is actually the normal beam, direct normal. And then let's say, for example, you're walking down the street. There is a steel plate or something on the street. Okay. You won't be able to take a look at the you won't be able to take a look at the steel plate because it kind of hurts your eye. That is because of the reflected beam. You're not looking directly at the sun, but you're looking at some of the reflected beam coming from the steel plate, right? So it also hurts your eye. So those are the two different components which we need to make sure we need to understand. So what happens is when you have a module that is tilted at 10-degree tilt, what happens is it receives some of the direct beam from the sun, but it also receives some of the reflected beam, which is reflected by cloud and everything. It's not like only we all know that we are seeing certain things because light is reflected off of the object, right? We see whatever we see is all the light that is reflected by the object, but it doesn't mean that if you're looking at TV, it doesn't mean that only TV is visible to us. We can see everything around it because light is everywhere. It's all reflected and it's come to us. So that is what this 7.7% gain you see is because of all of the reflected light and direct beam that's hitting on the PV module. So and then this one, global incident below threshold. So what this means is, we have, each and every module has a parameter, right? They have an efficiency. So what happens is some modules are made for, say, regions like Rajasthan, Gujarat, where they have lot of high energy insulation coming in, right? So they may not perform really well at low light. But there are some modules which are good to be performed, which have good performance in low light conditions, like for example, curtains, indoor region, and they may not perform well when they are put outside in open sunlight. You might have seen this in some of the satellites, right? When you look at the solar array that is present in the satellite, it's not just one region. It has more than one layer of solar. So what it means is, it reacts to different spectrum of sunlight. Right? The very first layer might convert all of the 1000 watt per meter square region. The second layer might just look at 600 watt per meter square and all those. So what happens is this module is optimized for say 1000 watts per meter square. But what happens is at most of the region, most of the time we are not reaching the 1000 watts per meter square. We are seeing somewhere around 850, 700, something like that. So what happens is your efficiency changes with that. It's just like a vehicle. We have a mileage, right? We see that in the advertisement they say it travels 50 kilometers per liter of petrol at 60 kilometers per hour speed, right? So that is the efficiency curve that they have given us. But what happens is when you're traveling at 70, obviously your fuel efficiency is going to come down. And let's assume you're going to travel at 120. Obviously it's going to come down much. So that percentage loss you see, because in the efficiency that is something similar. So all these modules are optimized for 1000 watts per meter square of sunlight, but sometimes you're going to get 700, sometimes you're going to get 1100, something like that. So what happens is throughout the year it simulates and then tells you that this is the loss you have because your site has a very varying insulation. And then this near shading loss. You remember when we were in the orientation tab, we chose 10-degree tilt, 186 azimuth, and then we were playing with the tilt angle. And then in the shadow losses we saw a 1.2%. So this 1.1% you see here is that value. And then this is IAM. I told you about the incidence angle modifier. So we are keeping a 10-degree tilt. So only at certain times during the day, the sun is going to be exactly perpendicular to the module. And rest of the day, it's not going to be perpendicular. It's going to be at an other angle. So whenever it is not at perfect perpendicular to the module, you're going to see some of the energy loss due to reflection and refraction, and this is the loss. And this is the soiling loss. So what happens is, after all these losses, you arrive at this point where it says the 1422 is actually, you're adding 7.7% to it, and then you have all of these losses, and then this is the final energy you have, 1400 kilowatt hour per meter square, right? And this is the overall area of the module, right? We have 5112 modules, right? Oops. 77 inches times 39, right? Into 2.54 into 2. So 1.93. So 1.93 meter square is the area of each and every module. You multiply that by 5112, you get 9905. I think this module has a different different spec than what we have. So let's assume, I think it's 1.99. Okay, so this is the module area, right? So what this means is, 10193 meter square is actually the collective area. Collective area means area of each and every module times the total module count. So you have this, and then we know that the efficiency of the module is 18.06%. So this efficiency comes from the PAN file. If you have a spreadsheet, something like this, you can go and see the efficiency. It says 18.1, 18.3, 18.6. So we are using a 360 watt module, and the efficiency is 18.1, and that is what we see here. Right? So we have this value, right? Let me show you calculation. So we have 1400 kilowatt hours per meter square. The overall area is 10193, right? So this is the energy we have as sunlight. So this is all the energy we have from the sun striking on the modules. But we know that the module's efficiency is only 18.06%. It has the capacity to convert only 18.06% of sunlight into electrical energy. So you would divide this by 100, and then so 2577 kilowatt hours. This is in megawatt hours. So you divide this in by 1000. Right. You have 2577.19, and that's the number you see. So till here, it's all sunlight. We are doing all these losses in the sunlight spectrum. And here is where the energy is converted from light energy to electric energy, right? And this is where you have this one, 2577. So all these losses you see here will be in the electric spectrum, which says, okay, irradiance loss, temperature loss, quality, and everything. So what does this one mean? PV loss due to irradiance level. So as I mentioned, your module's efficiency is at 18.06% only when the sunlight is 1000 watts per meter square of irradiance. When the incoming sunlight is not at 1000 watts per meter square, let's say at 800 watts per meter square, 600 watts per meter square, obviously you're going to have some loss, and this loss accounted for over the year is 0.8%. And then we are going to look at PV loss due to temperature. As I mentioned, we are going to use only the light aspect of sun. We don't want the heat aspect of it. So, but we cannot completely get rid of it. The modules are going to get hot throughout the day. It's just like a car engine. It goes fast. It takes in gasoline, converts it into movement, but it gets hot, and obviously when it gets hot, it's going to lose a little bit of efficiency. It's similar here. They're losing energy because of the increase in temperature of PV module, and that is what happens here. We're losing 3.2%. This is based on the factor that we defined. We said 20 and 1.2. It is based partly on that, and it is also based on the ambient temperature, right? Let's assume you're in a AC room. You have a cup of coffee. It gets cold much faster because the temperature difference between the two is high, so it loses energy faster. It loses its heat faster. Let's assume you're sitting outside, you have a similar cup of coffee, but it doesn't lose its heat as quick as it does in an AC room, because temperature difference between the coffee and ambient temperature is not much high, so it takes a time to get into the equilibrium. Something similar to it. This is a cold area. I know your temperature loss would be much lesser. If it's a hot region, it cannot send the heat out, right? Your module has to lose the heat. If it's a cold area, your module loses the heat much faster, so you would see much less loss of energy here. But whereas if you are placed in, say, Saudi Arabia, right, your ambient temperature would be much higher than 25 degrees Celsius. It would be somewhere around 40, 42, 43. So there is no place for the module to actually send its heat out. So all of the heat is going to be trapped underneath the module, which reduces performance of the module. So you would see something like 11%, 12% if the project is located in Saudi Arabia. And then we saw about module quality loss, where we spoke about the flash data and what the final module wattage would be. So since this is not a loss but a gain, you see a plus value here. And then we defined LED loss at 2%, and that's what we see here, the mismatch loss on wiring loss. You might remember that the ohmic loss that we defined is at 1.5%, right? This is 1.5%, 0.5%, and transformer losses. But you can see that the ohmic wiring loss has come down to 0.8% instead of 1.5. That's because 1.5 is the maximum. But throughout the year, you're not going to see 1.5. There are some days where there is not going to be much voltage current traveling in the wire. So only when the wire reaches its maximum capacity, you're going to see some loss. If it doesn't do that, then we don't see any loss. Then it will be zero. So throughout the year, PVsyst averages the ohmic losses, and this is what the final loss will have. So and then you see inverter loss during operation, which is 1.9%. This is the loss. This is the efficiency of the inverter. The one that we used is 98% efficient, so we are seeing 1.9% loss here. But if you are using like a central inverter that has the efficiency of say 95%, you would see a 5% loss. And then same with AC ohmic losses. So this is DC wiring loss and this is AC wiring loss. So we define 0.5%, but throughout the year the average is going to be much less, and that's what is 0.2%. And then we have a transformer in the system. Obviously, transformer has to convert the energy from say the voltage from say 480 volt to 12.47 or 11 kV, 4.67 kV, whatever the case is. So obviously during that conversion, we are going to lose some energy because it's not 100% efficient, and that's why we see a 1.8% loss here. So you could see that we started at 2577 megawatt hours. We lost all these energy, and then we end up at 2294 megawatt hours. So this is the loss graph that we see in every single PVsyst report. So, and this number is what you see in this page, 2294 megawatt hours, and this is the specific relation. So this is what we do for a rooftop system. I'm just going to unmute everyone now, and tell me if you want to go back to some of the things and take a look at it.
So Ram, in few of the PVsyst reports, there is a graph in yellow color.
Yeah. Do you have like a sample, or let me bring you one? Give me 1 second.
I do not have one. Like I want to understand how to read.
I should have one. Yeah, give me 1 second. I'll just give me 1 second.
I think that is model layout. Ram, I think he's talking about the sun directions.
Okay. Give me 1 second. Let's go back. Is this the one?
Yeah.
Yes.
Okay. Yeah. So what this means is horizon. Let's assume you have a PV system that is right next to a mountain. Okay, you have a mountain range. It doesn't have to be right next to it. It could be like say even 100 kilometers away. But what happens is, unless and until sun comes above this, your module is not going to see any sunlight, right? Um, it's only going to look at scattered rays. It's not going to give you a direct beam. Let me draw one. Assume. Hold on 1 second.
Okay.
Let me show you this. So what we're going to do is we're going to draw. You're going to generate a shading object. Okay. Let's assume we're going to do. In PVsyst, you cannot go and draw a mountain or anything. So what I'm going to do is I'm just going to draw a regular parallelogram, something like that. Okay?
You make a structure. I mean to say the
Yeah.
pole.
Yeah, something like that. I'm gonna do that. Okay. Okay. So let's assume this would be a mountain, and then we're gonna place modules here. Okay. So I have a module here, right? Sayan, are you able to see the screen now?
Yes.
Okay. So this, let's assume this is a situation that we're talking about. Okay. So we have a mountain range here. We have a PV module here. So what happens is, sun goes from east to west, right? So during the morning hours, until we come here, until noon, the mountain is actually to the other side of the module, right? And here it is all clear. There is nothing blocking the sun's view. There is nothing blocking the module's view from the sun. So you won't have any shading loss. But what happens is when you get here, mountain is here, the module is here. So if the sun is actually very high in the sky, you would not have any problem. But during the evening hours where sun comes down, when it comes here, it will be usually very low. So what happens is direct sunlight would not hit the modules. It will always be scattered beams. Okay. So what happens is, that is something, if it is something close by, let's assume you have a tree nearby, you have a electric pole. What you can do is actually you can go and model that within PVsyst. But when you have like a mountain that is 100 kilometers away, you cannot really do that, right? So what happens is we depend on something called as, Meteonom. Meteonom has a tool called horizon tool. So what it does is when you say a location, it takes into account the surroundings, and then it generates a report for you which gives you the peaks and drops. So what I'll do is I'll show you the tool, and then we'll download a sample data, and then we'll bring that within PVsyst. Okay. So I'm just going to go to demo mode. So this is the tool. This is Meteonom. Okay. In Meteonom, you can use this particular tool for free. You can download Horizon for free. So I'm just going to click on this option, which gives me a map. I'm gonna go to Chennai. I'm gonna go here. I'm gonna click on this. It says Madras weather station, everything. So what I'm gonna do is I'm gonna choose something like this. Let me see if we get a bit more granularity. I'm not sure. I'm just gonna put. Okay. So we are here, right? So once I've located the site, I'm just gonna click on create new location. So I do this, and then I just save the name as Tamram Chennai. And then I close this, and then I come here, load this site. Okay. So do you see this one? So what
Yes.
it says is, okay. So if we want, I'll go back and tell what we did within Meteonom to get this one. But we'll just, let's just look at this one. So what this one means is you see a couple of yellow lines here, and then you see degrees over here. You see degrees over here, right? So what this means is, hold on 1 second.
Okay.
Can you guys hear me now?
Yes.
Okay. My earphone came off. So yeah. Okay. So when you see this, what it means is these numbers, the number 8, 10, 12, 2, so these all means time during the day. Okay. And this green area, this means it's shaded. So what this means is when you're looking at from ground, when you have a plane that is facing perfect south. So when you go to this side, and then when you're looking south, so what happens is this degree, this means 8 o'clock, 10 o'clock, 2 o'clock, right? So here, if you see, you don't see any shading at all. It is all good. But what happens here, this is 16, this is 17, 5, and this might be like 6 o'clock, okay? So after 6 o'clock, you're not able to see the sun, okay? This is for certain times of the year. This is like the one that is closest. The shortest one might be the shortest day in the year, and this might be the longest day in the year. So it is much easier if you want to see this image within PVsyst. So what I'm going to do is I'm just going to save this one and then bring this one within PVsyst so that we can visualize it much better. I close this one. We close this one too. And then you see option here which says horizon. I'm going to click on this. I'm going to click on the read import data. So before importing the data, I'll show you, say what this means. You see a pendulum type value graph here. So
Yes.
this is the path of sun. We might have seen some online pictures where a certain person takes picture of the sun from the same spot throughout the year. You would see that it actually makes a 8 shape. It is what you see here. So what this means is this 8 type structure you see, this is time of the year. Okay, and this line, this inverted bell, this bell shaped line which you see here, actually corresponds to each and every month. So what this means is the innermost one. This month is actually, I think it's March or June. Let me get you a better data. So this one corresponds to 1 month. This line corresponds to 1 month. This line corresponds to 1 month. Okay. So this is the default graph we have, and this is called azimuth and sun height. So it moves from 0 to 90 degree as you see. So what this means is, usually during sunset, sun goes down, right? It's 0 degree. At sunrise, it's at 0 degree. So during the day, sun rises up. It goes from east to west, that is azimuth angle, and then it goes from 0 degree to 90 degree, which is altitude angle. So the location of sun during any point of the day. Let me show you another graph which makes it very clear. This one. The image was the best one. Okay. When you look at this image, you see this is the sun, right? When if you want to go out and see the sun now, you have to look at the sun at a particular. You have to move your neck to see the sun, right? So this angle you make is called the altitude angle. And when sun just rises, it's at 0 degree. During noon, it's at very high, and then it goes down for sunset, right? That is the altitude angle. And then there is another factor called as azimuth angle, and this is the azimuth angle. So what this means is, if you're looking perfectly south from your house during the morning hours, sun is going to be at your left hand side, right? So if you want to see the sun, you have to turn completely left. Let's say you go out again and then you want to look at the sun at 10 o'clock. Okay, so you don't have to look all the way to the west. You don't have to look all the way to the west. You have to just maybe turn 20 or 30 degrees from perfect south. So that angle sun makes is called azimuth angle. So what happens is, if you want to define, because this is three-dimensional, right? Sun moves in a three-dimensional space. So if you want to define the location of sun, you have to define it in two ways, like what angle it makes with south and how high it is in the sky, right? So how high it is in the sky, it is defined by altitude angle, and what angle it makes with south is what you define by azimuth angle. So what happens is, so in PVsyst, this is defined. This one is defined for a site. What we're going to do is we are going to bring the detail that we downloaded it, a Meteor. So when you click on this, it gives you different options. PVsyst internal file, Carnaval file, Solmetric Suneye, Horizon software, and Meteor software. So Meteor software is what we use at the moment. I'm just going to click on that to bring this value in. Okay. So you see the value now. This one doesn't have a lot of value. So what I'm going to do is I'm just going to adjust this one. Okay. I'm going to pull it like this. Okay. So let's assume that we downloaded a Meteor file that has something like this. Okay. So what this means is, this is 8 hours, 6, 7 o'clock, 8 o'clock, 9 o'clock. Okay. And this month is actually December. This is, the sun's path is usually divided into 7 sections in a year. Okay. I'll write this thing down. Okay. So December is separate. Okay. Okay, something like this. Okay. So what happens is, this line you see, the lowermost line, it is for December, and the highest line you see is for June. So you know that, December 21st is going to be the shortest day in the year, and June 21st is going to be the longest day in the year, and rest all is going to be matching of two. For example, sunrise time on February is going to be similar to one in October. Sunrise time in March is going to be similar what you see in September. So these are all in pairs. So December and June is going to be separate, and rest are all in pairs. So what happens is, you have a mountain that is something like this. So what it means is, you're looking at this line, the innermost line. This is December. And then you're looking at this 8 here. This 8 means 8 o'clock. Okay. So it is in shaded region. So what this means is, at your particular site, at 8 o'clock in December, your PV module is going to be shaded. Okay. It is going to be shaded up until 9 o'clock, and then it doesn't see any shade. And then this yellow region here, you follow through in this line, and then you go till 10. 10 is fine. Again, you go till 11. What it means is, okay, at 11 o'clock you're going to see shade. and then till 12 o'clock you have shade, and then from 12 to 1 you don't have any shade, and then from 1 o'clock till evening you're going to see shade. Okay, this is for December. Let's assume we are looking at June. So we go with the outermost line. So 6 o'clock we are going to be shaded, 7 o'clock we are shaded, 8 o'clock we are shaded. But after 8, we don't see any shade at all. Okay, till sunset. And same goes for other months. Let's assume we are looking at November. So this will be November. Okay. So November we don't see any shade here, but at 8 o'clock we see shade and it goes down. Let me use this in the report and see how this changes. Right. You see the thing now? Let me zoom in. Okay. So as I mentioned, 7 is 22nd December. Okay. 6 is 19th June and 22nd November. So what it means is this line, the second line from bottom, represents both January and November months. Line 5 represents February and October. So what this means is if we are looking at, say, line number 5, it goes from here. So what this means is our particular PV system is going to be shaded at 7 o'clock during both February and October. Okay, and then it goes to 8 o'clock. It's going to be a little bit shaded. It's shaded till 9:30, and then after that we don't have any shade in this particular month. For the month of February and October, we don't have any shading losses in this time of the year between 9 o'clock and 11 o'clock. And after 11:15, we are still seeing some shade till say 11:30, something like that. And then there is no shading from this time to this time, and then again you see shading. So this is how this graph is used. So for there are a lot of sites. For example, there are some sites which don't have any shading at all. If it's like, say, a country which doesn't have a lot of hilly regions, like deserts and all, you could go for miles and miles without having any hilly region or anything like that. So in those areas, you would see a flat thing. That it means the outer atmosphere. Outer atmosphere. What it means is like the vegetation over there. It doesn't give you any problem. It's not a hilly region, so you don't have any problem with horizon. But there are some sites where you might have a hilly region right next to the project, or even like 100 kilometers away. That might give you a little bit of problem like this. What we have done is we have exaggerated here, but usually you would see a curve going from here, something like this. Okay. Let me import one sample that might have a better representation of what happens in the real world. Let me find one. Let me use this one. This one is good. It doesn't have anything. Look, this one. You see it's flat throughout the day. But what happens is during the evening, after 7 o'clock, there's a little bit of shading, and before 6 o'clock in the morning, there is a little bit of shading from the surrounding regions. It's fine. Okay, this one is completely flat. We're not seeing anything at all. So let's try Ooty. Okay, let's try some hilly region. So do you have any place in mind where you saw a lot of shading from horizon?
Not exactly. I tried to understand this graph, but I could not.
Okay.
So now it makes a lot of sense how it works.
Yeah. So what I'm going to do is let's try some hilly region and see what really happens there. Okay, you see, it is this bag, right? It has a little bit of shading in here. Because we are already at the top of Ooty, we're not seeing a lot of shade.
Maybe you can take Coimbatore.
Yeah, it's close by, right? Okay, so this is where the hilly region is. We are right here. I'm just gonna move this one somewhere like this. Okay. So I'm keeping it Hold on 1 second. No. Sorry about that. So we are seeing a site. So what I done is I kept it closer here. Okay, so we have mountain region to the east of it. Right? This is south. This is east. Sorry, to the west of it. Let's see what happens. Or I might push it here. Okay, so it's right next to it. I'm just going to create this region as sample mountain and close this. You see, it has changed completely because
Yep.
we are right next to a. I'm just going to save this one and close it. I'm going to import this data here. Right. You see, it has completely changed the whole system. So from 5:30, it doesn't matter which month of the year, it's always shaded. But in the morning hours, it's a bit better because you saw that the mountain regions are located to the west of the site. It is not in the
Right.
east. So what happens is east is fine. East is morning hours, right? So it's fine. But in the evening hours it's bad. But let's assume we are in northern hemisphere, right? If we were in southern hemisphere, what would happen is it would still be the same. It doesn't change much. But there might be some location where you have like a enclosed mountain right below you. In those cases, you might see throughout the day. Even during here, you might see some shading loss. And then I just run the simulation. Right. So you see it, here we have all the shading laws. Here we don't, even though it's being shaded here, it doesn't matter because it's all behind the plane. It's like when the sun comes to 12 o'clock, sun is already risen here. Sun also goes up high the sky, right? So we are okay here.
Right.
But let's assume if sun doesn't rise at all, let's look at countries like Norway, okay, where sun doesn't go high in the sky, it just stays at one level, that it just rotates throughout the day. In those cases, sun might go something like this. The whole area, even this region might be a bit flat. Okay, ours is all a perfect dumbbell like this. But
Can
some regions. Yep.
can you pull up for Norway? Let's
Yeah,
just
it's take a
for
look.
understanding.
Yeah. What I'm gonna do is hold on 1 second. I'm just gonna tools. I'm going to change the site from Newark to something in the Scandinavian. You see, this is the path I have pulled in. Okay, this is the graph we would be seeing in the final phase. Okay,
Okay.
you saw how our graph went up till 90 or 75 degree. You know, it was like a huge bell graph. And then here you saw the gap, right?
Right.
But in this one, you're not seeing that because sun doesn't even raise above 45-degree height.
Okay.
So when we go out in the noon, like 12 o'clock, we'll have to look exactly
Straight.
perpendicular to the sky to look at the sun. There it is 45 degree. Okay.
Okay.
So and
Right.
how you see it doesn't go to zero at all. You see in the
Right.
end, it's always at a certain degree. So it means that even during night, you would be able to see a little bit of sun. Okay. That's
Okay.
why
Okay.
this graph is like this.
Okay.
I'm
Okay.
trying to bring
Got
this
it.
one into the yeah. Let me pull in some good site in. I'm not finding any meteor station nearby. So what I'm doing is I just go to download meteor sites. So what this means is, for this one, we have a site, okay? But as I mentioned, for any site, we need to have a file associated with it. So what PVsyst does is, it just has a file name. It hasn't executed it. It is not in a format that we could use. So what I did is, we go into this part. We go into this section, databases, and then you see something called synthetic hourly data generation, right? You click on this, and then this is the station we were trying to use, right?
Right. Right.
Then you see something in the bottom, it says execute generation, right? You just click on that, and then a site is created. A meteor file is created for this site, right?
Okay.
So then I close this. Now if I come here, I'll be able to use that file. You want to remember the name?
Ram, I think I get the point. So this is clear.
Okay, 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 cool. So
Quite
what
good.
was the next question you had? Anything else that is not
So
clear?
another request is the Excel sheet that you have created. So I think you can share that as well after the meeting.
Yeah.
Would
So
be
what I'll do
helpful.
is I'll put this in a better format because this one doesn't have any explanation in there.
Okay.
Let me put this together in a way that we could just understand as we're looking at it. It has all the values scattered throughout. So I'll just put this in a better format and then I'll share it with you.
Okay. Next question is, so when we were inserting the azimuth degree in the PVsyst initially,
Yeah. Yeah.
so can we take it as a thumb rule that any side that is in the northern hemisphere, we have to just subtract 180,
Yeah.
and whatever the
Yeah.
number comes in,
Exactly.
we just put it. For south, it
Yeah.
will be exactly the way the number it is, like the southern
Um,
hemisphere.
it still changes. What happens is, so let's assume this is north, south, east, west, right? So if you look at any architectural drawing or any site plan, usually what they say is north is 0, and east is 90, and south is 180, okay? And west is 270, and again it's 360 or 0 at north. But PVsyst, what it does is it's like, okay, if you're in northern hemisphere, south is perfect 0, okay? I'll tell you this. Okay, so this value in yellow is what we see in real world. Okay. Now PVsyst, what it says is south is 0. Okay. Right. So if you are going to the east, it is negative. Okay.
Right.
So 90 degree would be minus 90.
Right.
Okay. If you are going to the west, it will be positive. So this will be 90. So 270 is 90 degrees from 180, right? So it's 90. And then when you go here, it's a total 180. Okay. So you won't even be able to define that. It's like completely opposite. You're not going to see any sunlight at all. So you won't be defining that. Right?
Right.
So this is what we see. This is for southern hemisphere. This is for northern hemisphere. Okay. But what happens with southern hemisphere is that it changes a little. You cannot just do by minus 80. So what happens is this will be 0. Okay. So when you go to the east of it, it's like you come a dial. You don't. When you go to the east of it, when you rotate clockwise, it's always like that, right? So you go this way, it will be 90, and then this way it will be minus 90. So when you go clockwise, it's 90, and then you go counterclockwise, it's minus degrees.
Right. So for the sites that are in the southern hemisphere, so what would be the number? Let's say in the like the site diagram, the PDF which you had opened up.
Yeah.
Let's say it is in southern hemisphere, then what's the number that we will be inserting?
So what I'm going to do is, let's say, I'll pull up a site so that we can visualize it and check it. Okay.
Okay.
Do you remember any site in southern hemisphere?
Never dealt with any.
Yeah, exactly. Give me 1 second. Let's just make sure that we are choosing a site in southern hemisphere. Okay, let's look at Cape Town. Right? So this one, let's go to this one because it kind of gives you a better clarity. Okay. You see, they have moved this thing. So this one is north, and then you see west is on the opposite side, east is on the opposite side. Okay. So what they're saying is this system is facing perfect north, and let's assume we have a system that is, say it is north, and then it's facing a little bit of northeast. Okay. So what we should be doing is, from the spreadsheet that we have here, let's see, we know that the module, the thing is going to face like this. is there? Yeah. Let's assume it's facing like this.
Shapes.
Okay. Is this arrow good enough for you, or do you want me to put something else? Okay, let me bring in a broader arrow. Okay. So modules are facing like this.
Northeast.
Northeast.
Okay.
Okay, and the site is in southern hemisphere.
Okay.
So let's assume this is 0 degree, this is 90, this is facing 45 degree. Okay.
Okay.
So from our assumption, we should be putting in positive 45, right?
Right.
Agree? Let's
Yes.
go here. So we should be, this is north, this is east, and module is going to face like this. Okay, so it's not the positive thing. It needs to be negative, just like what we did in the previous. So
Just negative of that.
Just negative of whatever value we get.
Okay.
Okay. So if this one is say 55, it should be more. Okay, 55. So whereas it goes in the opposite direction, it's like 55, 45, whatever. But what happens is, let's say if it's here, if it's facing here, then it has to be whatever angle it goes, we have to separate that. What I'm trying to say is, if it's like this, it'll be just the positive of that.
Negative of that, right? Or what?
When it goes to the northwest.
Okay.
This is perfect 0, right? Perfect north, and then it's facing like this. Let's say 10 degrees. So that has to be 10, right?
Okay. Okay.
So if it's facing something like this, 55 degrees, it has to be minus 55.
Okay. Okay.
So since most of the projects that we deal with are in northern hemisphere, this is a better thumb rule that we can use in cases.
Right. Right. Okay. Okay. Nothing much from my side. Some question.
Okay. Is Vignesh online?
Yeah. Yes, Ram. I'm online.
So you wanted me to show about microinverters, right? So what we'll do is, you could see that I'm on the system definition stage, So where we defined, you saw where we defined SMA inverters. Just like that, you just go use the drop-down box and then you define a.
Just we have to.
Yeah.
Okay, microinverters we have to give an inverter section. Right?
Inverter section, that's it. So what I'll do is, N-phase is one microinverter I know. I haven't come across anything else. I'm just going to N-phase, and then it gives me all the details here, right? It tells me all the details I have. So I just choose a model. Let's say I'm choosing this model. So it depends, right? Sometimes one microinverter might take in two modules. Sometimes one microinverter might take in only one. So I'm assuming this one takes only one. So this numbers needs to be changed to 5112. And then it says modules in series is 1, module number of strings is 5112. Then you use it. That's all you do. And then when you use microinverters, there is one parameter which you need to get rid of, right? If it's a string inverter, you have different modules, so you have like a mismatch loss, right? But when it's a microinverter, you don't have the mismatch loss, right? So what you do is you go into this module quality mismatch. This one you just make it 0. Okay? Because you don't have that mismatch loss anymore. You're getting rid of that mismatch using the microinverter.
Yeah.
Right?
Yeah.
And then there is another type of system which we do, which is solar edge. You might have come across it. So what Solar Edge does is it has an optimizer for every single module we use. Okay. Let me choose Solar Edge inverter. I'll just show you what happens. So Solar Edge is a regular string inverter, but it combines the properties of a string inverter and also a micro inverter. Okay. So what happens is you have an optimizer connected to every single module, something like this. Okay, and then you have an inverter. So what happens is you connect from the module, the wire goes to the optimizer, and from the optimizer, the wire goes to the inverter. So when you choose Solar Edge, you could see that this section, it was a lot different before. Now you see it has optimizer input, inverter input, and all those. Okay. So what happens is, let me bring you a system that has Solar Edge design.
These things like SLDs are done using helioscope, right?
Which one? The layout?
Like layouts. Yeah.
No, I use Sundat. We at Sun Edison initially developed a tool. It is a plugin for SketchUp. So you have SketchUp, and then it's a plugin, and then I use that to generate layouts.
Okay.
Yeah. I mean, helioscope is also good, but sometimes when you want let's say for example you want to define multiple string sizes. You have like two systems, you want to define multiple string sizes. It doesn't give you that sort of flexibility. So I don't really use helioscope. And then there are other things which we cannot do in helioscope. For example, when I have this layout. Okay. So if I want to, let's say for example, if this module is here, let's say I just want to add like one module over here, then I may not be able to do it. Let's say this area, okay, this area is shaded, right? You see a black line here. It's because I've done the shading analysis here. But I'm like, okay, if there is a choice where I have to place either one module here or remove 17 modules, okay, then I'll be like, it's okay. I'm just going to place it one module, and I'm okay if it's also getting shaded. Yeah. But in helioscope, I won't be able to place that module because helioscope algorithm thinks that this area is shaded, and I have asked helioscope not to place any modules here. Okay. So it doesn't let me place a module here. So what happens is, if I am like, okay, I want to place a module here, so I'm going to modify the shading loss. I go and remove the shading loss. What happens is, everywhere, wherever there is shade, it removes that and places module there. So, it kind of doubles the work for me. So I kind of avoid helioscope for now. But there are projects where helioscope is easy. You just define it goes and builds it very, very fast.
Okay. Can you tell me the name of the software once again? This one?
Sundat.
Yes,
this is the name.
Sundat. Okay. SUNDAT.
Yeah, SUNDAT. I'll forward the link also. Right now, it's when we were Sun Edison, there was a team that was developing the tool. Now this is part of Forefront Power, and they are sending, they have like a monthly license or annual license for the tool, and then they just have it.
Okay. Trial versions are available, right? For this, we can use, right?
For Sundat, they give you a trial of 10 days, I guess. But there are ways. If you want to use the tool for a little longer, you can just tell them. You're looking at the tool, and if things work well, then you might go for a license or something. They might give you like a longer trial period. So they are still in the initial phase. They are trying to find users. They don't have as much user like helioscope. Helioscope is widespread. Aurora Solar, you might have come across Aurora. That is also brilliant.
Yeah.
They also have a very wide fan base, user base. But Sundat has very limited user base. Only people who are working for Sun Edison, who have gone out of Sun Edison, are still trying to use that tool. So they still have a long way to go. So if they find people who are interested and people who are willing to use the tool in their organization, they might even extend the trial period to a month or something like that, and they let you analyze the tool and come to a resolution.
Okay. Also, can you share that soiling loss sheet, like a slide, right? Like
Soiling loss
sheet.
Yeah. This is a proprietary Sanderson sheet. So
Okay. Okay. No problem.
Wow.
I think for now we can live without it and learn the PVsyst first, and then when we are okay with them,
what
then
I'll do
we
is,
can.
what I'll do is I'll try to find the article, the scientific article based on which this spreadsheet is developed. Yeah, I'll try to find that article and then forward it to you, because I'm still on a contract with Forefront Power. So this tool was put together from Sun Edison, it has moved to Forefront Power. So sharing this might violate their contract and I might get into trouble.
Okay, no problem. Just I want to know about how they are calculating this.
Yeah. It is not. It is not something that they have funded. It's just that they have put together the entire spreadsheet. So
Okay.
And there is another thing which you guys might have come across on a very, very frequently. Okay, it is called an 8760 file, right? 8760 data you might have come across. So what that means is every single hour it is something is generated, right? Energy is generated, but the output is stored in a spreadsheet. So when you see the final page here, which says hourly data storage, batch simulation, optimization tools. This is where you come and then you click on this output file. Okay? You click on the output file and then you have lot of details here. It says meteor data, collector data, everything, right? So whatever happens, like when you go into efficiency, when you click on efficiency, it says efficiency of array, efficiency of inverter, something like that. And then you click on system, it says available energy at inverter output, AC ohmic losses, energy injected into the grid, all these values. So whatever values you want, you just click OK, and then click, and then just run the simulation, right? So what happens is, PVsyst will generate a spreadsheet for every single hour. Okay. Usually what we look at is the final report, right? It says this much energy is generated. This is the specific yield and everything. But in order for you guys to use, like especially in monitoring, you guys generate a lot of reports based on that, right? So you definitely need an 8760 data. That's what we're generating right now.
Okay.
So how would this real time we can start here and we can fetch the estimation?
What Krishna? I lost you a little bit there.
Yeah, just if you have a real time like last month or before month,
Okay.
how we can
okay, there are a couple of ways to do it. What I have done predominantly is when you have like a monthly data, okay, you need two data. You need DHI and GHI, right?
You want to say diffusion?
You need diffusion and
how?
no, you usually get direct normal. What are all the data you get from pyranometer? I think you get GHI and direct normal, right?
GHI and POA. Plane of array.
You get plane of array. Okay.
No, plane of diffusion is available.
Yeah.
We get only one feed, depends on at which angle we are installing it.
So you get only plane of array, right?
Plane of array.
So usually just with plane of array it's a little bit difficult. Okay, what we need to do is we need to have plane of array and direct normal.
Actually, for direct normal, there is different hardware that has to be installed at the site.
Is it? I thought usually you have like more than one pyranometer, one measuring DNI and one is plane of array, isn't it?
Generally we used to have GH and POA, but diffusion nowhere we are calculating.
Okay.
Yeah, I heard that diffusion is one of the key points which is required to calculate the real time.
Yeah.
But
so what I used to do is, whenever I get the data from field, for example, if someone gives me data for just 1 month, what I do is, you remember the file that we imported in, right? What I do is I go there, open that file, and then replace the data for that particular month with the data we have in hand. For example, all other years, January to November might be the original data that I downloaded. If I have data for December, I just replace the data for December with that and then generate a report. Okay. And then what I do is I just compare the data from December. Okay. I take only all the data from December and then compare it with the site measurement. So I will click OK. What I'll do, I'll show you the sheet now. You see, we created a project now. We tried to generate an 8760 file. So this is the spreadsheet you see. It has everything like this. You just go and right. So this is the data that's generated. You have global horizontal, diffuse horizontal, and this is for every single hour. Hour 1, hour 2, something like that. And then you have system file, E-grid and everything. So you see E-grid, E_grid. This is the energy that is being generated. Okay, this is all the energy that is being generated. And you're seeing some negative values here because it really depends on the inverter. Sometimes you have some inverters consume a little bit of energy. Inverters need some energy, right? They need some connections because they also have some hardware running, displays and everything. So during the daytime, you don't see negative energy because solar is generating energy. It consumes a little bit for its own operation. Very, very minute, but it consumes a little bit. But what happens is during night time, you don't have solar to balance that. So it obviously takes from the grid. That is the negative energy you see in the 8765. But this is not the case with all the inverters. There are some inverters which have night disconnect. So night time when there is sunset, that's it, done. It will be sleeping. It wakes up only when there is sunlight again the next morning. So when you have something like night disconnect, you may not have this much of loss. But there are some inverters which don't have. Yep.
Sorry to interrupt. Even in those cases, there will be some consumption. The reason is it will keep on checking the reference voltage from the grid line.
Yeah, exactly.
One more question I have. So let's say for multiple MPPT range, how if we select multiple MPPT, how many it will vary? Like, how it will refer? Like whether it is a different wattage of modules it will refer, or in the site specific, is there any shading will it refer?
Okay. So what happens is, if you want to define multiple MPPT, let's go with this. So let's see. So I'm going to use a Selectria inverter. Okay, I'm just going to say 80 kilowatts here. On inverter. Okay, this inverter actually has 2 MPPTs. I think so. I'm not sure. It might be the case. Okay, this inverter has actually 3 MPPTs. Okay. So what I'm going to do is, I have 12 strings. Okay, and I have 3 MPPT. So what I would be doing is I would be feeding 4 strings to each and every MPPT. But let's assume I'm going to use this particular inverter for 2 different systems. Okay, one half of the system has Hanwha 360 watt modules, and other half of the system has let's say a different let's say instead of 80 I have 55 kilowatts here. Okay, 55 kilowatt. I'm going to use 2/3 of the system. 2 of the 3 MPPTs I'm going to use for Hanwha modules. Okay. And for the next half, I'm going to use 1 MPPT, right? So I'm going to give 1 and then something 4. Okay. So you can see that I have different string sizes. So like this overall inverter is only 1. Here it is 2 MPPT, here is only 1 MPPT. So overall inverter is only one, but we have defined it for two different systems. You see, when you look at the thing here, it says Q peak maxima.
Yeah, can you zoom in?
Yeah.
Enough.
Yeah. So it's here. You see, it says array 1, 2 MPPTs. So since this inverter has only 3 MPPTs, it is 33%. Each and every MPPT is 33%. So 2 into that is 40 kilo, and then 1 MPPT. So overall you have only one inverter, but we are defined two different systems here.
Yeah, I understand. So another point is, let's say you have assigned here with the two different wattage or something like that. So within the site, if you see the if you consider which is lesser than where we can have a shadow losses, that MPPT will affect again, right? How it will will it take automatically as a default, or how it is?
So what happens is, it really depends. So what we do as a practice is, for example, if there are certain modules that are going to be shaded, what I do is, when I install the system, I try to keep all of the shaded strings. Some strings are shaded, some are not shaded. So all of the shaded strings kind of go to one MPPT. So even if one MPPT is performing bad, I'm fine with that. Okay. But what happens is, in PVsyst, at least for now, you don't have the opportunity to say which module gets connected to which MPPT. You have like an overall shading loss. Let me bring you a drawing inside. So you know how I create the whole layout in in SketchUp, right? I draw the whole drawing, with the modules and everything. And once I do that, what I do is I try to bring the whole system into PVsyst. Let me show you which. I don't have a project in hand. So what I can do is I can.
Ignesh, can you go on mute? Or somebody noise?
Okay. So I have a project here for which I had a SketchUp drawing, right? You can import the whole 3D from SketchUp into PVsyst. So I exported that from exported that from SketchUp, and then I'm importing that into PVsyst now. So PVsyst is going to bring the whole drawing inside. You see, this is a drawing. Okay, this is the layout I had. This is my module. This is all the abstractions I have. Okay, right. So what I'm going to do is, what happens is, in SketchUp, when you're drawing the system, we actually define very regular azimuth, right? Because SketchUp, AutoCAD, everything takes real world into reference. So north is always 0, south is always 180 degree. So, but what happens is, when we bring a project something like that inside PVsyst, it doesn't understand that it is generated in a different tool. It takes that 186 as azimuth and then completely rotates the whole scene. So what I would have to do is, I would have to select the whole scene and then just rotate the scene so that I have correct azimuth. So it would be like say something like 25, not 226. Something like this. Okay. So now when I see, these are all my modules and these are all the abstractions, and everything is abstraction except for the module. Everything else is going to cast a shadow, right? So what I'm going to do is I'm going to run the shading analysis now. I'm going to run the shading animation. You're going to see that. On the right side, you can actually see that there is some shading from 8 o'clock to 10 o'clock, and then the shading again starts at 4 o'clock till evening. So you can see the module. This module, blue color is not shaded, but this is all completely shaded. There is this region, there is this huge unit which is casting shadow on all these modules here. Okay. This is on, say, June 21st. I'm going to choose December 21st now. December 21st is the shortest day and you're going to have maximum shading. So I'm just going to run the simulation. You see how it simulates for every single hour, and then you have a much more shading loss. I'm going to remove this. So if I remove this, I think you will be able to see the shading loss in a much better way. These are all the modules and these are all the shading.
Yeah, it's clear.
Right? On the right side, you will see a graph. Okay. So this animation you can run for 1 day in a year and see what happens. But when you close this one and then just checking the whole distance and everything, what happens is you can just create a table and then use it for the whole system. So 1 second. Okay.
If you have a area, so that we can make this kind of SketchUp. Right?
Yeah. You can make a SketchUp. You can place all the modules and then bring that into PVsyst and run the analysis.
Okay. If we give the switch and table numbers, it will automatically populate, or how it is SketchUp?
In SketchUp, it depends, dude. It depends on it depends on the tool that you use. So sometimes it's okay, sometimes it doesn't do that. So let me try this. So when I click on table, okay, so now we have the shading scene. I'm clicking on table. So table is when it calculates all the shading loss. It says, for example, height of the sun is 90 degree. When height is 90 degree, it means sun is at the highest point. You won't see any shading, right? However, if it is like, even if whatever happens at noon time, sun is going to be right on our head, right? But whereas in the morning hours, you see some shading loss. So this table is created. You close this one, and then when you run the simulation, it takes into account all the shading losses. So you would be able to see the final shading loss would be completely different from, you remember when we were defining tilt and azimuth, we were saying what is the interrow space and everything. You don't have to do any of that. If you are drawing a 3D scene, you don't have to do any of that. It picks up everything. It picks up module count, picks up module size and everything. It picks up and then brings to this page. Now you see there are two images. One is this.
Yeah.
Okay, and the other one is this. This is the drawing of our layout. See, this also comes in the report.
Okay.
So only if somebody is uploading this 3D diagram, it will come, right?
Yeah, exactly. Only when you have a 3D diagram. But for tracker system, you definitely need to do a 3D drawing. Okay. It doesn't have to be the exact.
I mean, with the area, we need to place all the rows and modules, and then only we have to, no? And we need to do manually, right?
Yeah, for trackers, you don't have a choice. You have to go and create manually. So what I have been doing is I create one. For example, I'm using Next Tracker. Okay.
Okay.
The ground coverage ratio or the distance between two modules is always the same, right? Unless I change it for every project, unless I change for 50% GCR, 35% GCR, something like that. If I'm going to change the ground coverage ratio, I have to change it. If I'm using the same one, what I do is, for example, I create a system size for 500 kilowatt. Okay, I know 500 kilowatt will have so many modules. So next time when I want a 2 megawatt system, what I do is I just copy that and paste it 4 times. So I get like a 2 megawatt tracker. And then if it's 10 megawatt, I just copy it and paste like 20 times. So I get like a 10 megawatt tracker. So that's what I'm doing for tracker at the moment.
Okay.
So Sayan, you see this sheet here. We are not using horizon. We are not using horizon, but this sheet is actually for the shading loss. So what it means is, you see on the left side, you would see something that says shading loss percentage, 1%, 0.5%, 10%, 20 and 40%.
Yeah.
It all corresponds to these lines here. One is dotted line, one is long dotted, one is solid line, something like that. So what it means is, at this during this time, the lowest line is 40% shading. So 40% shading, it means in December before 8 o'clock or something, it is always shaded. Okay.
Right.
Shading is throughout the day. But we need to understand that since it's southern hemisphere, right? You would see the number going from right to left. Right side is morning, left side is evening. Because we defined Cape Town, right? We haven't changed from that. So the system still thinks that we are in Cape Town, and you could see it is going from here.
Dude, this shading analysis you do for only rooftop or grid utility also?
I do for ground mount also, but it really depends. If there are a lot of trees and things like that, then I do shading analysis.
But you need to
But
manually give the rows and rows. Those things are you need to work out a lot, right?
Yeah, I do that in the layout, and then I bring it in. So all the
Because let's say if it is 50 megawatt, then it is too huge, no?
It will be huge. I won't be able to bring in a 50 megawatt system. What happens is when I bring in PVsyst doesn't say what is the limit. Okay. But if you bring in a system that is 3 megawatt, it just completely freezes. It won't do any work for you. So what I do is for example, if the system is like 100 megawatt, I bring in a megawatt of system inside. So it is more like representative. The system that we brought now, it is a 400 kilo system. It is fine. It doesn't have any problem. But remember, we had a system of 1.8 megawatt, right? Even if I'm bringing that SketchUp file inside, it will have problems because it has to simulate for every single module. Okay, and we have 5,000 modules. Even for a small rooftop, we have like a 5,000 module system. So it takes time. It runs algorithm for 5,000 times and it keeps on running. Imagine a 100 megawatt system where we have like 1 lakh modules, right? It doesn't really have the engine built to do that.
See, I have here a question. Let's say if I have maybe a utility big scale project, but though I have some of the locations have shading due to some, let's say, a pole or something. Only if I can't do that only per particular location.
You can do that. So what I've been doing is
maybe not for entire side, maybe for the particular, let's say,
exactly. So what I have been doing is there was a project. So what happened is southern side of the project had a road. Okay. So in that road they had some lampposts.
Yeah.
Okay. So what we did is we just simulated the southern section. Okay. Where the electric poles are.
Yeah.
And we didn't bring the northern section inside. But what happens is you might get like this shading loss is all percentage, right? So what happens is, let's say you have a 2 megawatt system, out of which you are bringing in only 1 megawatt inside, which has
not even 1 megawatt.
Just for an example. So you have like a 2 megawatt project. You are bringing in only you are drawing 1 megawatt in PVsyst, okay, and you are seeing a shading loss of 0.5 percentage.
Okay.
This 0.5 percentage is for every module present in this system. But what happens is your actual system is twice the size, right? So the loss would actually come down, right?
Okay.
I think to answer Kake's question, we can do that. Just that we have to recreate that
particular section. Yeah, we just need to create only that section in PVsyst and then run analysis.
Okay. Cool. I think it's a little long session.
Yeah.
Good, good. The initial one would be good, but what happens is you
Really
guys
good.
just download a demo, take a look at it.
Yeah.
What I'll do is next time if you have any questions, just write to me, and then we'll
Yes.
have a session to answer all of the questions, so that
Yeah.
sometimes Kake might have a question that Sayan might not have come across, but will come across once he starts designing a system. So let's have a
Machi,
session for that. Yep.
yeah, I have a question like that. Earlier I was discussed
Yeah.
technology like tracker and fixed in the same site.
Yeah.
One thing,
Yeah.
another one is oversize, like 1.6
Ah.
or 1.6 times even more. Let's say 1.7 ratio DC.
Yeah.
That is
Yeah.
one. Uh, uh, yeah, these 2 points.
Okay, okay. I'll note it down, and then
Mhm.
we can maybe circle back again sometime next weekend
And
and go
on top,
over that.
next session maybe you might covering with the tracker and separately and seasonals
Yeah,
separately.
yeah, exactly. Now we just did a rooftop. Next time what we'll do
Yeah,
is we'll do a tracker,
right.
which changes little bit of these settings. The orientation we might change a little bit, and then get to
Mm-hmm.
tracker. And then while doing
Yeah.
that, what I'll do is I'll also try to cover what each and every factor means here. For example, we haven't done anything with miscellaneous tools.
Yeah.
Miscellaneous tool, you can define power factor, you can say P50, P90, you can say grid power limitation. Sometimes there is a grid power limitation, right? So what happens is you might have like a 2.5 megawatt system, but the nameplate detail is only 2.25. So whatever goes above 2.25, at any point of time, you guys might have come across some of the sites while monitoring, those prison sites, like Corcoran,
Mm-hmm.
Comanche and all. So what happens is you cannot put any power into the grid. So it always has to feed the local. You cannot put power into the grid. So what happens is they might keep monitoring the load. So you
Yeah.
cannot put more than 2.25 kilowatt on the grid. So you limit it here. So what happens is even though the system is producing 2.5 megawatt or 2.51 megawatt, you limit the system to 2.5. So the 0.01 is actually a loss. You cannot get credit for that.
Mm-hmm. Okay.
Okay.
So what I'll
Yeah.
do is I'll forward the recording we have for this session, and then
Okay.
I'll take in questions. Some might have thought this is a little bit faster or something like that. So maybe let's circle back again, get together, and try to answer all the
Actually,
questions anyone has. Yeah. No, I think I lost you.
Yeah. So I think there was a wonderful opportunity for us learning the PVsyst. And thank you so much for spending so much of time
No.
continuously speaking.
yeah. Machi,
No
like,
problem. No
are
problem.
you sharing this video anywhere?
Yeah, yeah. I've recorded it. I'll just download it and then send it to you.
Yeah, if
Well,
you can
I'll
share
share
the
the
link,
link. You guys download
because I
it.
have so many
I'm
times
also
got
planning
disconnected.
to, yeah. I'm also planning to download this and then upload into YouTube, so that even if you don't have the link, you should be able to see it. But I'll see how big the videos come up to be.
Yeah,
I
it's
think the
about
video is
2 3 hours.
like 3 hours, so I'm not sure how big a video I could upload to YouTube. I'll just take a look at it. I'll
Okay.
try to maybe trim a little bit of the first 15 minutes, and then probably the last 10 or something like that, and then try to upload it to YouTube.
Yeah. Yeah.
Okay. That's awesome.
Okay. Thanks, guys. Take a look at it. Let me
Yeah.
know if you have any questions.
Yeah.
I'll try to get back to you with answers as soon as possible. If not, we'll have a session sometime, say in the next, before the next 10 days, and then we'll clarify all the questions.
Okay.
Thank
Makes
you very
sense.
much. Thank you very
Okay.
much.
Yeah.
Thank you.
Thanks, guys.
Thank you so
Thank
much.
you, Ram.
Thank you,
Have a
Ram.
good rest of
Thank
the
you.
day. Talk to you soon. Yeah.
Thank
Bye.
you. Bye.